transform on strings, which is at the basis of several compressed data structures for text processing. So given a text, it is defined as the concatenation of the last characters of all rotations of the text sorted according to the lexicographic order. So let's have a little example. Here we have the classic text banana. We have the list of the sorted rotations of the text, and then we can compute the BWT just concatenating the last character of each row. So due to the advancements of the NGS technologies, large string collections are becoming commonplace in bioinformatics. And this has so moved the focus towards the development of data structures which are able to specifically handle collections of strings. So in this context, the BWT plays a central role, since it allows efficient pattern matching queries while keeping the data compressed, if possible, in space proportional to the number of runs through the run length encoding. However, when talking about BWT of string collections, the things complicate a bit. The BWT is originally defined on individual strings, and it's not completely straightforward how to apply the BWT to string collections, since there are different methods we can use. Due to this, in the literature, there are several tools computing extensions of the BWT to string collections. And in an earlier work at CPM 2022, we show that these different BWT variants are not equivalent. We also show that the differences between the different BWTs also extend to the number of runs, and that these differences strongly depend on the input order of the sequences. So the number of runs, or R, is defined as the number of equal letter runs of the BWT. And this parameter is important because it allows to measure the size and the performance of several data structures based on the BWT, like the run length FM index or the R index. It also can be used as a tool for measuring the repetitiveness of a data set. So for today, we will focus on a specific BWT variant we called multi-dollar BWT. So the multi-dollar BWT can be computed concatenating the strings with implicitly different dollars. With implicitly different, I mean that the dollar in the memory are represented as the same character, but we break ties using the dollar positions. So the first dollar is smaller than the second dollar, and so on. Actually, we can compute this transform just sorting the conjugates, the rotations of this concatenation. So first, we have the rotation starting with the $1, then the rotation started with the $2, and so on for all the other rotation. At the end, we compute the multi-dollar BWT concatenating the last character of each rotation. So due to these features, all characters in the multi-dollar BWT preceding a shared suffix occur together in the same interval. So let's have an example here. Below, we have all characters preceding the $8 suffix. So because all dollars are different, the order of the rotations and of the BWT characters in these intervals depend only on the input order of the sequences. And for the rest of the talk, we will call those intervals, one of those intervals, having at least two different BWT characters, interesting interval. Since multi-dollar BWT depends on the input order, different permutations of the same string collection generate different outputs. So here we have the same string collection, but presented in 3 different orders. And as you can see, in the interesting intervals, you can have a different order of the characters, and you can have also a different number of runs. So at this point, we may wonder, does there exist an input order that allows to minimize the R value? So the answer is actually yes. And recently, Bentley et al. Presented at ESA 2020 a linear time algorithm for computing the optimal input order of the sequences. And I will refer to the transform computed with this input order as optimal BWT. So here we give the first implementation of the Bentley et al. Algorithm for computing this opt-BWT. I divided it in 2 steps. So in the first one, we used a size-like implementation for computing the suffix array and the sep array, which you have already seen in Giovanna's talk. And then we use the Bentley et al. Algorithm for computing the final transform starting from these 2 pieces of information. So let's proceed to step 1, computing the suffix array and the sep array. So our algorithm is an adaptation of the well-known size algorithm of Nong et al. With few differences. So we handle string collections instead of individual sequences, and we compute the sep array which was first introduced by Cox, Bauer, Jacobi, and Rosone in Bioinformatics 2012. So actually, this sep array is a bit vector storing the position of the BWT blocks containing rotation starting with the same shared suffix. So let's have an example. So first, all sep intervals start with with a 0, and then we have a 1 for all the other members. So here we have, for example, we have the interval containing all rotations starting with the $ suffix, and so on for all the other intervals. So for time reason, I will only give an high-level view of this algorithm. So I divided it in 5 steps. In the first one, we compute the types of the concatenation. So like in the classic size, so we have the L, S, and S star types. Then we use those types to cut the input into substrings called LMS substrings. And then we sort those LMS substrings in order to compute their lexicographic ranks and build a new string on which we will recurse again. So for today, I will skip those first 4 points, and I will show how to use the inducing step in order to compute the suffix array and the sep array. So let's assume we reached this point in the computation. And we know that for S prime, all LMS substrings are distinct. So at this point, we can initialize the suffix array. We can compute the buckets of the suffix array. So here we have 5 buckets, 1 for each character. And then we initialize the sep array. So first, before initializing the sep array, we insert the LMS substrings in their correct position. For example, here in the $ bucket. And then we initialize the sep array. So here we have a sep array containing 7 positions. Why is that? Because this is the sep interval containing all rotations starting with the $ shared suffix. So let's proceed to the induction of the L types. So we do this scanning the suffix array left to right. And each time we find a position that induces an L type, we put it in the correct position of the corresponding bucket. For example, 3 induces 2. 2 is a character A, and so we put it in the A bucket. Then 6 induces 5, D, and 10 induces 9. At this point, we can insert a 1 in the SEP array. Why is that? 5 and 9 are induced by 6 and 10, which belong to the same SEP interval. So what does it mean? That we are inserting on the left of a shared suffix an identical character. In this case, we are inserting D on the left of a dollar. And so we will have another shared suffix, in this case, D dollar. So let's go ahead to inducing the S types. Like before, this time we have that 9 induces 8 in B, and 5 induces 4. Again, like before, we put a 1 into to create a new SEP interval. Why is that? Because 4 and 8 are induced by 5 and 9. And so does it mean that we are inserting a B before the D dollar shared suffix? And so in this case, we will have the new SEP interval corresponding to the shared suffix BD dollar. Then we map back the suffix array and SEP array values, and we continue with the computation. At the end of this computation, we get the suffix array of the whole collection, we get the SEP array, or again of the whole collection, and at this point, using the suffix array, we can compute also the BWT. In this case, this BWT will be the BWT of the sequences presented according to the input order. So let's go proceed to step 2. So actually, Bentley et al. Reduced the problem of finding an optimal input permutation to the tuple ordering problem. So let's see how to compute the tuples. So actually, we can divide the BWT according to the SEP intervals. And for each SEP interval, we can compute the tuple containing the set of characters in the interval. So here in this first tuple, we have AT. Then for the second interval, we have ACGT, and so on for all the other intervals. I would like to point out that we can have a position outside an interval, and in this case, we will have a tuple with only one character, and then we can have an interval containing a single character. So again, you have a single character in the tuple, and this interval will be not interesting. So let's draw the list of the tuples. The tuple ordering problem consists in permuting the order of some of these characters in order to reduce the number of runs of the concatenation. So here, for example, we can put this A on the right side in a way that we fix the run break here between the two, the first two tuples. And again, we can move the T, this orange T on the left. And again, we fix another run break, and so on for all the other sequences. So we implemented this algorithm using a stack data structure containing the paric vectors of the interesting intervals. So a paric vector is just an array of integers containing, for each character, its multiplicity. So let's see an example of how computing this optimal BWT. So the first interval, we see the first SEP interval. So we inserted the corresponding paric vector in the stack. So 5 A's and 2 T's. Then we have the second SEP interval, 2 C's, 1 G, 2 A's, 1 G, 1 G, and 1 T, and so on until the C. So now at this point we can stop. Why is that? Because we know that the position of this C in the BWT is fixed. So we can compute the optimal permutation of the BWT up to this position. So let's look at the two top paric vectors. This match on the C, and so we output the 2 C's. Then with the next two top paric vectors, they match with a T, and so we insert 2 T's. Then with two last spark vectors. We have that the images on the A. We have 7 A's, but we see that the top Barrick vector still contains 2 characters, the C and the G. So first we output C and G, and then we output the A's. At the end, we get the optimal permutation for this segment of BWT. And then we can continue in this way for the rest of the BWT. So let's talk about the experiments. We did a test on a short rich dataset containing sequences of length 50 coming from the SARS-CoV-2 RBD region. And we divided it in different prefixes, where the biggest prefix contains 32 million sequences. So for each prefix, we measured the average run length of both the optimal BWT computed with our tool and the input BWT computed with GSoftSort, which is another well-known tool using a size implementation. So what we can see from the graph is that the optimal, the number run, the N over R of the average run length of the input order BWT doesn't increasing the size of the alphabet, while this is not the case for the optimal BWT, which reaches a value of over 100. So you may, of course, there are other input order that are better than the input order, but also the Colex BWT, aka RLO, get 2 million runs more than the optimal. We also measure the time needed for the to compute the BWT of all the different prefixes, and we saw that the overhead for computing this optimal BWT is little. It doesn't affect too much the performance. So to sum up, we presented the first algorithm for computing the BWT of a string collection that guarantees the fewest possible runs. We saw that the number of runs of the optimal BWT can differ significantly to the input order BWT. And we saw that the time and space we need to compute it are comparable with a well-known size implementation. So in the end, we submitted the extended work of this project with the title Computing the Optimal BWT over Large String Collections. And this is joint work with Veronica Guerrini, Giuliana Littaca, and Giovanna Rosone. So thank you for your attention.
Thank you, Davide. We have 6 minutes for discussion and questions. So are there any questions from the audience?
Hi, can you show again your slide on the time to compute the optimal BWT in experiments?
Yeah.
So that's a log scale, and I was just curious if you could tell us what's the factor for the largest point, maybe between the two, because it's kind of hard to see on a log scale.
Yeah. So. To be honest, I don't remember the exact factor, but it was a little over. So there is a little difference. Mm-hmm. It's below. I think a 1.5 factor is quite close, because here the idea of this experiment is that we would like to show that this overhead, that we need this extra work for computing the optimal BWT. This overhead is little. No, it's not. It doesn't affect too much the performance. So that was the point.
Okay. Hi. Another question. So this is a stupid question, but is it possible to compute the worst order? So maybe in order to say that in the best case, our algorithm improves this much,
So yes, actually, this is this is a nice question. So actually, having this stack, okay, you can also try to compute the worst order. How? So in this case, we try to pack the BWT runs and avoid the run breaks between the intervals. But actually, you could try to interleave characters, no? So you may output a C, then a T, then a C, and so on. So actually, you could also compute the worst.
Okay,
Yeah.
thank you.
Hi, Travis. So you can maybe guess what I'm about to. So can you do this? Any thoughts if you can do this with PFP? So prefix reparsing.
I was thinking about it when I started working on this project, and so I think yes, but it requires to to compute the separate to compute some extra information on the BWT of the parts because you need to know where the separate are while computing the BWT. And this information is not obvious, no, from the to obtain. Yeah, for actually for each when you compute the suffix array of the dictionary, you need to know if a suffix is shared or not. So yeah, I think actually it's possible, but I didn't work out. I didn't work on the details. Yeah.
Okay, thanks. Because we do have you can do the LCP stuff with the SA.
Yeah.
I think actually Max knows more about that than I do.
Yeah.
Hi, David.
Yes.
Thanks for the talk. Okay. Using induced sorting, you can obtain directly the BWT, right, without computing the suffix array. That will be a problem for you to compute the sub array.
So, so you mean computing the BWT and the separate without computing actually the suffix array?
Right.
Yeah, it's possible, and in our extended work, I don't know how much I can say. Okay, maybe if my co-authors will want to say more about it.
Davide, you can just say anything about our submitted work. I think it's submitted.
Okay. So we have an adaptation of the BCR algorithm in a way that we can compute the BWT and the separate without actually explicitly computing the suffix array. So I don't know if it's possible to do it with size, but yeah, actually. I know there is another implementation presented at CPM 2022, where it uses some of the I think it uses it's partially on external memory, and it uses some of the size to compute the BWT. And for example, this without computing explicitly the suffix array. And in this case, one could maybe just compute the suffix, the BWT and the separate directly. But here with the standard size, no, you first need to compute the suffix array because it's actually a suffix array construction algorithm. So
thanks, Davide. We can Thanks for the talk and very interesting discussion. So we can move to the next speaker, which is another Davide. Davide Cozzi.
Hey.
Can you share your screen?
Yes.
Okay.
Are you seeing this?
Yes, we can.
Okay, wonderful.
Okay, so next speaker is Davide Cozzi. Is going to talk about algorithms for the run length encoded positional Barrow-Wheeler transform. So
Yes.
please, Davide, the stage is yours.
Hi, I'm Davide Cozzi, and today I will talk about algorithms for the run length encoded positional Barrow-Wheeler transform. First of all, we have to clarify the context. Here we have a little example of a panel of haplotype, where every row represents an haplotype and every column a variation size. So from computational point of view, we can see that this is simply a binary matrix. We also have an external haplotype used as a query string, and we have to compute set maximal exact match in order to solve a sort of pattern matching task. Summing up, an haplotype is a binary and long sequence X sub I. A panel of haplotypes is a set X of M haplotype sequences, and an external haplotype is an n-long pattern Z. We must have an n-long pattern because our algorithm have to respect the position in terms of matches. In fact, a set match is defined as a triple A, B, E, such that X sub E has an exact match with Z from the column V to the column E for each I in the set A. A set match is set maximal only if it could not be extended neither to the left or to the right, and we cannot include any other row of the panel that can have a better match. From a biological point of view, every human being inherits an haplotype, so a set of allelic variants from the two parents, and this panel could be used for solving some biological problems such as haplotype estimation, genotype imputation, or genome-wide association studies that are looking for association between genetic variants and diseases outcome. We have a problem. Large panel of haplotypes require more and more memory to be analyzed. So we have developed a length encoded Barrow-Wheeler transform used to compute set maximal exact match computing with a very strong reduction of memory usage. We have tested our implementation on some panels from the 1000 Genome Project. We have to mention some important results in literature. First of all, Darwin in 2014 introduced the positional Barrow-Wheeler transform that can quickly compute set maximal exact matches with a strong trade-off in memory. In fact, if you want to query multiple external haplotypes, we need to store 13 nm bytes in memory. So to reduce this memory usage, we also used some results regarding the run length Barrow-Wheeler transform, such as the R-index and two tools, Moni and Phony, that strongly inspired our two algorithm for the run length encoded PBWT. First of all, we have to remember how this data structure works. Positional Barrow-Wheeler transform is built at each column with the colexicographical reordering to the previous column. So if we need to build the PBWT for the column 5, we have the reordering until the column 4. And this ordering is stored in the prefix array. And if we take two consecutive rows in this reordering, we store the starting column of the longest common suffix until the previous column in the divergence array. For those who are used to the Barrow-Wheeler transform, the prefix array corresponds to the suffix array, and the divergence array corresponds to the longest common prefix array. Interesting is to notice that similar haplotypes, for example, similar until common 4, so consecutive in the reordering, will have the same character in the next column. And the next column is stored as the PPWT matrix, and this is the information that we want to store in a run length way. So, in order to compute the set maximal exact match, we decided to develop different data structure that act as building blocks for our run length encoded PWT. Above, we have a mapping data structure, which contains all the information needed to follow a precise row inside our permutation. Then we have at the left the two components related to the monivariance of the PPWT. We have a component for thresholds. A threshold is defined here as the index of the first maximum value of the divergence array inside the index of a run, and we need a component for the random access to the panel. Then we have another solution that is based on the longest common extensions query. In this case, an LC query returns the length of the longest common suffix until a certain column between two rows in the panel. This could be easily computed using a straight line program that is a context-free grammar that allows us to compute these values. We need also two additional data structures. First of all, we need the prefix array samples at the beginning and at the end of every run. And we need a data structure that can compute the so-called phi functions. In our case, phi function returns the adjacent values of a certain value of a prefix array. In order to compute the set maximal exact match, firstly, we need to compute the matching statistics. Also, this theoretical concept has been redefined for the PPWT, and we define the matching statistics as an n-long array of pair row len, such that at each position, it stores the index of a row that shares a left maximal match, a len-long left maximal exact match with our query. We have also a useful lemma. In fact, if the len value in a set position of the matching statistics is greater or equal the next value in the len of the matching statistics, we could also guarantee the right maximality of the match. So we have a set maximal exact match with the row saved in the matching statistics array. Here we can see a little example. Look at column 5. We have stored 13 as row and 6 as len value. In fact, we have a left maximal exact match with the row 13 until column 5. And having that in position 6, we have 4 as len value, so 6 is greater or equal 4. We could report that 13 share a set maximal exact match with our external haplotype, our query. But we have other 3 rows that shares the same set maximal exact match. In order to report also these queries, we use the phi functions. The structure used to compute these two functions is based on a very simple idea. Two prefix array value will remain consecutive in our permutation of the PPWT as far as they correspond to the same character. In the image, green is for 0 and blue is for 1, for example. But when they correspond to different characters, their prefix array value have been stored in the prefix array samples component. In fact, the first will be the tail of a run, while the second will be the head of the next run. Using all this information, we can easily compute all the prefix array values in order to recognize all the set maximal exact matches. Regarding experimentation, we have tested 5 panels from the phase 3 of the 1000 genome project. These panels have a fixed number of haplotypes, about 5,000. And we have decided to extract the last 100 haplotypes to use them as queries. Regarding the number of sites, they have a variable number of sites. And for example, the panel related to the chromosome 1 has about 6 million sites. That's a very, very big number. Interesting is notice that the average number of runs at each column of the PBWT is, we don't have a lot of runs. So this is very useful for our solution because they scale both in space and time on the number of runs. Here we can say a little comparison of the memory usage of the components. Above in blue, we can see how much memory would use the entire divergence array if it would be stored. Then we can compare, for example, 2 solutions to store the mapping structure. We could use both sparse bit vectors, as you can see with the circle here, or it's hide inside this plot, bit compressed int vector. So in our test case, we can see that bit compressed int vector is the best solution. Also, we can notice how much memory requires the random access data structure if we use a vector of bit vector against the memory required by the straight line program. Talking about set maximal exact match computation, we have compared our solution with the official PBWT implementation by Darwin. And let's focus only on chromosome 1 due to the time. And we can see that his estimation about required memory have been confirmed in our test. In fact, for the panel related to the chromosome 1, we need 400 gigabytes of memory to use the PBWT. While our solution, for example, the one based on the LC query, requires only 4 gigabytes of RAM, while using random access with the bit vector requires about 8 gigabytes of RAM. Both solutions are using bit compressed int vector for mapping structure, and in that case also for the threshold. Regarding the time for the set maximal exact match computation, we can see that the structure based on random access and threshold is very fast. It requires only 150 seconds, while both the LC-based solution and the official PBWT requires about 1000 seconds. So we have defined a run length encoded PBWT that can compute set maximal exact match with a strong reduction of memory usage, but obviously there are a lot of future developments. First of all, Darwin, in his paper, proposed also a batch solution that computes the internal set maximal exact match between the panel of haplotypes and the panel of the queries. So he studied all the queries at the same time, while our solution query one external haplotype, so one query at a time. So we could think about some solution for handling multiple queries at a time, and also we need to implement the internal set maximal exact match computation. Then we could also think about other characteristics of the panel, such as a multi-allelic panel. So not based on a 0-1 alphabet, but a generic alphabet, but also panels with missing data memorized, stored as wildcards. So precise value that we don't know which is the correct allele to be stored, and it could be everything. For further detail regarding the theoretical results, our preprint is already available on bArchive, and our source code is available on GitHub if anyone wants to test our solution. Thank you for your attention, and if there is any question.
Hi. Thanks, Davide, for the talk. So are there any questions from the audience? And for the online attendees, you can raise your hand, and after that, we'll enable you the possibility to unmute yourself. So are there any questions from the audience?
Travis.
Hi, Davide. So I'm actually a co-author on this. So this is more of something that we should think about in the future. Oh, it's very echoey. So something else we've been working on, but I hadn't thought about it in terms of this, is we can find basically, so MEMS, but for us now, this would be set maximal matches. But we can also put a threshold on the frequency. So we can, this could be interesting if you had like one panel of sick people and one panel of healthy people. So at the moment, what we've been going through is doing this thing of like finding K-MEMS, which Gonzalo calls Q-MEMS. But we should actually look at doing that. We're working on the strings, on the DNA sequences. But now that I think about it, we should actually also look at doing this on the PBWT panels. But okay, so just I was saying that, so now it's recorded, so I won't forget. So there's a.
So we are thinking about K set maximal exact.
Yeah, putting a threshold, saying I want it to occur at least 10% of the time in the sick people, and at most 2% of the time in the healthy panel. So I have something archived about this, but on strings, not on panels. So we should think about it for panels. But now somebody else has probably thought of a question. That was to buy you some time, everyone else.
So do you mean we would look for example, in input we have a minimum number of rows that can share a precise set maximal exact match? It's correct what I understand?
Well, you're going to say, I mean, there are certain things where you like there are disease, something, and it's like you can't explain the disease. It's like not an on-off thing, but you can say, okay, this string seems to be associated with it. More sick people, like 20% of sick people have this thing. And so, but this is not for validating, and only 2% of healthy people have it. So you can have the variation, but it's less likely that a healthy person has it. But now this would be data mining for those strings where you say that where you set a threshold, and you. But we should talk.
Yeah. Obviously.
I just otherwise if I don't say this now, I will forget.
Are there any other questions?
I have one question, but in the, can you hear me?
Yeah.
Okay. In the matrix, in the binary matrix, how repetitive is the binary matrix, like split it into blocks, this one?
I don't make any test about the repetitions, and this is only an example. Real panels from 1000 Genome Project, just to give you some number, has 0.03% of ones inside the entire panel, because ones represent the minor allele. So real matrix are more sparse than this presented as an example to show. I think that this matrix inside has about 100 blocks or something like that, but I don't know I don't make any test on this value, so
Okay, thank you.
I cannot be useful.
Thank you.
Sorry.
There are other questions?
I think here no.
Okay, I can ask you a question. So you tested against the original implementation of the BWT. Are you planning on testing on other more recent implementation, like the one used in Qt 5, for example, or other inference tools?
I have no plan, but I think it should be very interesting. For example, there are some works by Nazeri, I don't know is the current pronunciation of his name, relating to leap data structure used to compute faster the set maximal exact match. And I think that I'll see on GitHub also a work named Syllabus BBWT that maybe I should explore. But
because
I have...
Yeah, it would be interesting to see the comparison on the size and time, and also see if it would be possible to incorporate this work, because I mean 100%, 100 times less space, it's kind of a good improvement. So maybe it could be applied to even larger data sets, like the 100,000 genome project in UK or things like that.
Absolutely. Thank you for your question.
Are there any other questions in the meantime? If no, we can steal a couple of minutes from Davide and jump to the next talk, which is on site. So is Fernanda ready?
Yeah, I'm here.
Yeah, but we need to share the slides.
Thank you. Well, meantime, my investigation is more applied, so it's way more informal than the previous presentation, so my apologies, but well, there it is. My name is Fernanda Sanquirico. I'm from the University of Chile, and my work is named Are Inserts on Genomic Collections on BCF format. And more, we want to achieve like compression over this format and add this query. So our motivation, we have been hearing this a lot those 3 days. There's nothing new under the sun. The data is growing very fast, and we must store it in a better way and execute queries in an efficient time. Plus, in particular, are related to DNA, genome, and sequencing is growing a lot. And we have a bunch of amazing compacted structures, and it's time to apply one more of them in the real world. In particular, as you can relate, we are going to work with BCF, which stands for variant calling format. And this huge format has mainly 3 parts. The first one is the meta information lines, which has a lot of information. For this work, we can skip a bit of it. Then we have the header line and the records. And the first section is a nightmare. It's not standard enough, so for the people who codes can relate, that is, I prefer to drop it a bit in this work. So first, the VCFs works over a reference, which is in FASTA format, and as you heard before, has the header part, which is the identifier, and the first part maybe over there. And for me, it's more important that part of the information, which is the identifier, and then the bases, which are the reference. There is. Maybe? Thank you. So now we will focus on the header and record lines. As you can tell, the header has the chromosome, relates to the chromosome, the position where our edit will be applied, their ID, which I will not care about in this presentation, the reference, the base which is located in the position, and the list of variants, quality information, which is important, but for this conversion, I will leave it aside. And statistical information, the format, and the end, the columns of samples, which tells if the variant applies in the current allele. So how VCF works, we have the reference, the record. For instance, we have this variant over the 21 chromosome. In position 10, the base C will be replaced with CA base in the first allele of our first individual. So we take that C, replace with that string, and put it over there. And that's it, in a very, very, very simplified way. My apologies for those who works with this format. I know this is not all justice, but and this format has a lot of relation with this index, which is relatively impulsive, which is a compressed index for highly repetitive sequence collections based on relatively impulsive. To be more precise, I will work with the variant made by Gonzalo and Victor. For us, if you want to construct this index, you would take a collection S of size n and a reference of size r over an alphabet of size sigma. And then how we manage S, and we compress S based on the reference, generating the impulsive factorization with zeta factors, and that will be stored in this expression bits, and allow us to find all the occurrence of a pattern or size m in a very efficient time. But the most important for us, if you want to know more, read the paper. My apologies, I don't have so much time. But more important for us are those lines. So keep in your mind the collection, the reference, and the factorization. So how do we connect BCF with RLC? And from BCF, we get the reference and recreate the factorization, which sounds quite simple if you think, like with the previous example. And the same happens here. Like I have the same substring from here within the reference, and we describe in like an explicit way the difference. And BCF is exactly that, and which sounds quite good. So how we create this whole collection for all of our samples or individuals? First, we define a chromosome like the concatenations of its alleles, in this case a diploid. And then the genome of each sample is the concatenation of each chromosome. And then our collection of individuals is the concatenation of the genomes, and so on. It sounds, this structure will be so important for these conversions. So, and then the factorization will be the concatenations of each factorization, which sounds wonderful. Like, yeah, it's all done. But we have a huge problem here. If you take a look here, we are looking for each individual concatenated, but BCF works in another way. And if you read the format for each record, you have variant and then sample, variant, then sample. So it's like a transpose situation. And in order to fix that, I implemented a 3-step conversion, which the first one is named parse, which takes the reference and the BCF format. And then we process the reference, recovers the base, and recovers the identification. This is a way simpler example, but we will remember the relative pose within the full reference and its length. This is quite minimal, but in the reference we have all the chromosomes. If you want to work with genomic collections, then all the chromosomes will be connected in the full string. Then we will generate all the combinations over the alphabet ACGT of size 1 and 2. In practice, we will do it with size from 1 to 4 because in BCF we have explicit bar edits. This index in its constructors don't support explicit edits, so we will concatenate all these into the reference. And then we will pass to the VCF, and for each line, I made this structure which has these 3 columns are for identification and then characterization for the edit. So for the first line, we know that for the 21 chromosome, position 10, the base C, which has length 1, will be replaced with this chain, and it's applied to our first 2 individuals in the first allele. And that's why important the combinations, because this expression is stored in our reference, and we know that it's at position 24 with length 2, and so on. And we keep working, and that's it for that step. But if you remember again, for the previous description, we work with this structure. All these phrases are stored in binary files, so we must sort them in order to create this in text. So with that externally memory sort algorithm, we sort them first. We must sort them for sample for this column, then for chromosome, then for allele, and then for position. And that's how we read them directly. So that's sorted, and then we pass to build, which receives our phrases and the reference, and now we are able to build the factorization. First, for each edit, we must complete with the part of the reference that we are going to keep, and we continue. For example, here we have for the first individual, 21 chromosome, first allele, or edit start in position 10. So we must keep this part of the reference and insert the edit. And so on. It's quite too easy to get it, but with this description, we have in one full string all the samples. We must remember where it ends when we want to recover the original positions. So we generate all the factorization, but we must remember the end positions of each allele. We don't care about which chromosome or which sample, only remember the end of each allele. We pass this information to the constructor or RLC, but again, we have a quite huge problem. The constructors needs the full chain. And by sure, we don't want to recreate the full genome again. That's why we have BCF, not the plain sequence. But here, another little piece of work that I changed the constructor, because if you want to know something about the original sequence, take a move through the factorization and then go to ask to the reference. We don't want to recreate this. And it worked. And then the constructor gave us, which I named the VCF interpreter, which will save those end positions, which will be a sparse bit vector with rank and select support, because with that information, we can recreate the original position. In this case, for example, again, we will remember this structure. For example, if we want to ask if we found a pattern inside the index will return to us these positions, but those numbers doesn't mean anything to me. But if we execute this list of operations, for example, the pattern in position 25 happens, as you can tell, in the first allele of the first chromosome of the first sample. So we can transform this number into this 3 characterizations, and that's how we can recover exactly in a precise way where and exactly which sample, allele, and chromosome, and so on. Of course, there are a lot of border cases which are not described here. If you want to know more, and soon I will release all the source code in GitHub so you can check there. And our experiments, we tested over the dataset builder on 1000 genomes project over the 21 chromosome. And those are pretty little, but when you process them, if you recreate virtually the full text of the genomes, you have those length of text, which is quite huge. But after the parsing, we reduced from 2 to 1 radio compression, and the error index reduced to 4 to 1 radio compression. And which is useful, we are even less as a reference, and those BCF are between like 20 to 8% proportion from the original sequence. In the time conversion, it works quite fast, parse and sort, and for those data sets, doesn't take more than 1 minute. But again, another problem. And build the index takes between 3 to 14 hours to build for a smaller data set, way smaller data set. And why? We try this with real data sets like the all autosomal chromosomes over those individuals with those size. That's wrong. In fact, that was supposed to be a 2. And if you take a look here, the virtual length is really huge. In the code, you must use unsigned long for be able to process that information. And it was weird because I tried to index those datasets and doesn't work. We made a linear regression here, and apparently, if we try to process the most, now I get it. I've discovered that if you press the middle button, then it stops to work, maybe. Well, in the previous, this dataset was for 12 individuals for all autosomal chromosomes. And if you try to convert them, it will take like a 3/4 of a year. It's awful, it's unusable. So, and this happens because this index works with a grid of prefix and suffix. For you saw that those length, it takes a lot. We studied how much comparisons of characters we made for each string, and takes like a mean of 64, I think. It's a lot, even with optimization. So here is, in conclusion, it works. But it works reasonable in practice only for a small data set. It's good, but it can be better. If we sacrifice coverage or precision, we can discard the grid. The grid allows us to find patterns within phrases, like between the concatenations of the reference for the full text. But if we don't want to sacrifice that precision, it's an open problem to find a better approach for building the prefix-suffix grid for large text, or even better, replace that structure. As a mission for the future, never use this structure again if you want real applications for your structure. So that's it. Thank you. Any questions, donations, whatever are welcome.
Thank you, Fernanda, for the talk. Very, very nice topic. And I kind of dislike the conclusion, but so are there any questions from the audience?
I like the questions, donations, complaints. So very echoey. I'm just thinking, so we did a while ago, really a while ago, like 2014, we had a data structure called the hybrid index. And it was a mix of the FM index and the RLZ index. So basically the problem with it was you had to fix the maximum pattern length. But I think that what you would do, at every LZ77 phrase, if you say you fix the pattern length at 50, you'd go left 50 and right 50 and extract that substring, and then you concatenate the extracted substrings, and then you FM index it. So you wouldn't use the grid. So I'm just thinking you could probably, we did it with the RLZ. You could do it with any kind of string attractory thing. String attractors I don't think existed back then. But yeah, you could do it with VCF. So I mean, so we did it, and Dominic, Kempa, and Hector and Simon had an Linux paper more recently on that. So there should be a nice implementation floating around. So if you just take this stuff, and before you do the grid construction, instead of the grid construction, you sacrifice, you bound the pattern length. But it sounds like maybe you're doing that when you give up the coverage. And so if you throw it in there, it might work nicely fairly quickly, with this nasty caveat that you bound the maximum pattern. Hector claims that in practice it's not a problem you can chain, but it's like, yeah, that's in practice.
Yeah, in fact, we discussed it with Gonzalo, like maybe, and because in order to sort, you must read the prefix and the suffix, but you can read a fixed length in order to sort, and it might work, but it has that restriction that maybe you can try to sort a quite shorter pattern, but if you exceed this length of pattern, we can sacrifice that. If it's more big, you might pay a longer execution. But it's an idea. Thank you.
Are there other questions?
No.
Okay. Oh, sorry. Go ahead.
But I have one question too, because I don't know if I lost something, but you have in that file several references, no?
Yeah.
And you have to concatenate all of them in one reference, or?
That's why, well, I dump a lot of information, but in those binary files, you will remember the full reference, and then and that little dictionary of it there. Behind Maximiliano in the presentation, that dictionary is relevant because I made the same idea with the full S collection. You must remember which part of the reference, but in practice, inside the index, we don't care about it because that factorization made all the work. Here is how I remember which part of the reference, and that's the main job of the parse step.
Thank you.
I have a question slash suggestion. I don't know if you look at it, but how do you? So my main question is, how do you handle overlapping variants?
Sorry.
Like, you know that in VCF you can have overlapping variants that are compatible. They are called compatible, or basically the first variant overlap with the second variant, but they share the same prefix, so they can co-occur in the same position. So do you handle those? Do you filter them out?
In fact, I tried to study a lot about VCF, and yeah, there are those quite terrible variations inside VCF. And no, in order, sorry, but it's my undergraduate work, so maybe it's quite a little approach. But for simplicity, we only support simply variants, maybe those and SNP, because in VCF, in fact, the rearrangements are technically possible to convert here too. It's exactly the same logic with the factorization, but with overlapping, you must if you want to make it possible in code, you must remember all the possible overlappings that might happen. But it's for another iteration for this tool.
Yeah. Now, what I was going to suggest is that if you are going to work on that, like handling overlapping variants and stuff, you may look at the source code of HTS-lib, which is the standard that defines it's inside SemTools, which is the standard that defines the VCF. And there is a piece of code there in the consensus section, so of the part of the consensus command, where basically you can go and see how those overlapping variants are handled and how those are like taken care of. So which basically is, it's not written really anywhere. How do you deal with those variants? But it's inside the code. So it was just a tip.
Okay, thank you. And Travis?
Other questions?
Yeah.
Me again. So this is actually, I'm slightly concerned because I think I may have just asked a student to do something that I thought was easy and you may have just said was hard in practice. So for doing something or other, so basically for constructing a grid, I was asking them, I was looking at RLZ and I was saying, so what you can do is compute the Karp-Rabin hashes. So this is for like the sorting stuff. So I was saying, okay, first thing to do is you compute the Karp-Rabin hashes of all the prefixes of the reference, which is linear time, and the reference is small, so you can afford to store these. And you can sample them and fake it and bluff. But basically, suppose you have the Karp-Rabin hashes of all of the prefixes of the reference, and then so this way you can get in constant time, because you just basically do a subtraction. You can get the Karp-Rabin hash of each RLZ phrase because it's a substring of the reference. So you just take the substring, you like knock off the hash of the bit that you're excluded, you take the whole thing, you get the Karp-Rabin hash of the phrase. And then you can compute the Karp-Rabin hashes of the prefixes of the whole thing that end at phrase boundaries. And that way, since given any substring of the whole text, you can chop it into a suffix of a phrase and then a sequence of complete phrases. And that starts at a phrase boundary and ends at a phrase boundary. So you can get the Karp-Rabin hash in constant time of the sequence of complete phrases. You can get the Karp-Rabin hash of the suffix of the phrase at the beginning because it's substring of the reference. You can get the prefix of the phrase at the end because it's substring of the reference. So you can compute the Karp-Rabin hash of any substring of the text in constant time. And this is still working in space proportional to the reference plus the number of phrases. And that way you can actually do a comparison of any two substrings of the text. So I think I told a student to use this to do something quickly recently. I'm a bit worried because it sounds like when you were saying constructing the grid is actually slow. So can you do that Karp-Rabin hashy stuff to build the grid quickly, or have I just like sent my student off accidentally on a suicide mission? Does this sound plausible? I mean, yes, it sounds plausible that I asked my student to do something impossible. That's very plausible, but I hope my student isn't watching. Yeah. Okay, but did you try something like that? Because this, I think it should, I mean, basically VCF is a restricted form of KR. So this should work for what you do.
Maybe we can try. Maybe Gonzalo wants to add something to the discussion.
No, we didn't do that, but what we did was to check that we weren't comparing the same string of the reference, the same substring of the reference during comparisons of the sorting. Meaning it's perfectly possible when you are doing the sorting of the phrases that you are actually comparing two phrases that point to the same position as the reference, and then the string comparison takes a lot of time. We control that. We verify that we are not in the same position of the reference, and in that case, we know that the result of the string comparison is equal. So what you see there is the time for what I would say random strings comparison. I mean, the fact that it's a repetitive set is not the problem. We are taking out that. And even so, how many symbols were we comparing on average?
64.
Yeah, yeah.
With variance like 4,000, maybe.
Yeah,
It's,
okay.
But I think this should anyway. I can. So this way you can do a comparison in constant time because you can find the length of the. Oh no! You have to like binary search for the length of the longest common thing, and then you find the mismatch character at the end, and then you can do it. So yeah, you're able to do an equality check in constant time,
but not for binary search.
Yeah. Okay. I should warn my student.
there's a little.
Okay.
A little.
Coffee
For the coffee break.
Coffee. Okay.
Yeah. Thank you very much to all the speakers of this session. We are running late for the coffee break, and we will push the next session by 5 minutes. So we will start at 11:25 in Concepcion time. Thank you all the speakers of this session again, and see you after the coffee break. For all the online people, you can grab your own cup of coffee.
See you.
Sorry, we cannot ship the coffee to your house. Okay.
So bad.
for strings which have gaps inserted in them so that their cumulative similarity across all columns is as high as possible. And in this MSA, we can see that although the pattern AT occurs 4 times in these strings, those occurrences only span only 2 columns of the MSA. So yeah, that's a phenomenon that we usually see. And so we can reformulate the problem, and so we want to pre-process the pan genome so that later, when we are given some pattern P, we can quickly list the set of locations where the occurrences of P start. So not the actual sequences to which the occurrences belong to. So let's briefly go through the basic building blocks of our solution. So the first one is the R index by Gaggi et al., which is based on the run length compressed Burrows-Wheeler transform. And what it does is that it efficiently locates a single occurrence of our pattern P within the input string, and it works within the space bounded by the number of runs of the BWT. The second one is a data structure which allows longest common extension query, and that is a query that for 2 integers I and j returns the length of the suffix, the length of the longest prefix of the suffixes starting at ith position and jth position, so ith and jth suffixes. And the third block is, well, basically, our solution, our problem is very similar to the document listing problem. So the document listing problem is basically we want to preprocess the input strings S1 to Sn, so that given some pattern P, we can efficiently return the set of such case that Sk contain P. And for this problem, efficient solution exists. For example, the one by Muthukrishnan from 2002. And so this is also a block that we use. And to describe our solution in high level, well, as an input, we take the multiple sequence alignment, and afterwards we compute something that we call the column array, or call array for short. That will be described later. And afterwards, we run length encode this column array. And then for the query, we take the pattern P and we obtain a single match of P using the R index, or it can also be any other index. Our solution is not dependent on using R index. And then afterwards, we binary search for the interval which represents the occurrences of P inside of that column array. And after that, it's just a matter of using the document listing data structure to return the distinct columns. So let's look at this approach in more detail and with a concrete example. So here we have the same MSA as we have seen before, and we will also construct this string T, which has all the sequences from the MSA without gaps concatenated in it and delimited by the $sign. And also there is one hash sign at the end. And what we do now is we compute the suffix array of our string T. So here in this figure, we can see the actual sorted suffixes in 2 columns of our string T. And each suffix is being annotated with the column and the row of the multiple sequence alignment where the particular suffix starts. And what we do now, okay, so on the left we can see the first half of our sorted our list of sorted suffixes. And what we do is we take each run inside the column array, like the run of 5 5s that we see here, and we only store the start of the run and the end of the run. And the annotations of the rows with that. So for example, for this run, highlighted as red, we store the rows containing column 5 and row 5, and then column 5 and row 3. And on the right, this is already the run length compressed column array, and we can see that we only have those two rows for the run of 5. So this is the compressed version of this first half. Okay, so that's how we run length compress the column array. And now for the query, let's pretend that we are given the location of some pattern, let it be 80. And what we want to do next is we want to find the interval of all the occurrences of the pattern 80. Now, in this figure, we have highlighted by green the longest common prefix with this one suffix, which has the pattern B, which was returned by the R index as our location. And what we do now is we want to find the interval which represents all the occurrences of our pattern 80. So we do that by the binary search, and we essentially compare the longest common extension at each position with our current current suffix that was returned by the R index. And this way, also, when we look at one character after the first mismatch, we know which way to move. So we compare this position. Let's pretend that this first half is also the whole list of sorted suffixes. So this is the interval in which we start, and we compare this suffix with the one that we have been returned. And we see that we have to move down because the current one is lexicographically bigger or smaller. And yeah, so we move down. And once we jump down, then right now we can see that we are at the boundary of the occurrences of the pattern 80. So we stop our search, and this is the upper boundary of our interval. And analogously, we can also find the lower boundary of our interval. And right now, when we have these boundaries of our interval, then we just query our document listing data structure to return the distinct columns in which our pattern 80 appears. Okay, so we have implemented this solution in Python. Particularly, we have implemented the construction of the column array, and also we have implemented the binary search query, but with a naive LCE computation. And we have experimentally observed that the column array is compressible, as can be seen on this table right here. So we have tested this for some samples of multiple sequence alignment containing genomes of SARS-CoV-2 virus. And we can see that basically, even though we couldn't really run our code on larger MSAs, but we can see that the results are kind of promising, and that the column array, the number of runs of the column array is not really much larger than the number of runs of the BWT, which gives us hope that our index will be small. And okay, so the future work should include re-implementing our approach in a faster language than Python, for example, C or Rust, and using a smarter LCE data structure, for example, the one by Boucher et al. From 2021. And what would be really interesting is that so far we are limited to multiple sequence alignment, but what we would like to do is we would like to figure out how to compute an equivalent for the column array for a pangenome graph. So that would be the next milestone. So that's everything from me. Thank you for your attention, and I would be grateful for any questions and suggestions.
So, any question?
Yeah. Hi. Thank you for a very interesting talk. I have a question about the number of runs of the BWT.
Yes.
Unsurprisingly, yes. Okay, so in your last column, that's the number of runs of the BWT of the concatenated string where you concatenate with the same dollar and a hash.
Yes, yes.
Okay, so as you may be aware, this is not a fixed number. It depends on the input order.
Yes, we are aware of that. Yes, it's probably needed to take it with a grain of salt, I think.
Okay,
so,
okay.
Yes.
So because you just took the order in which the strings came, right?
Yes. Yes.
So very
well. I think there should be sorted lexicographically. Yeah. But yes, it's the basic BWT, so it's not eBWT. So
no, it's fine. It just so this is what maybe you saw David's talk this morning. So there is an optimal order, but if you take the lexicographic order of the input strings, that's bad. But if you take the collex, so the lexicographic of the reverse, that's already very good. So you don't actually have to do the optimal. But if you just take it, okay. But not in this way of concatenating. So not if you concatenate with the same dollar and a hash. This is the alternative way, and this is completely different. So the output is completely different from the different dollar one. So anyway, I just wanted to point out that that column is not really clear what it is. And of course, in your case, you might want to optimize with respect to something else, namely the third column here in the number of runs with the columns. Wouldn't that change also according to?
Well, so far.
Is that a variable column? This is the question.
Yeah. So far, it depends on the order of sorted suffixes. I don't know if. So the question is whether changing $1 to multiple dollar signs.
No, the question is if you. All right, is that column depends on the multiple sequence alignment you're using, right?
Yes. Yes. Yeah. It does.
It has nothing to do with the input order. Okay. But isn't that also maybe changeable? Okay, so I finished. Thank you.
We need to be not very unlucky, I would say. So, but the expectation is that it should be compressible intuitively. Okay, thank you for your interesting question.
So actually, continuing the same question. Adrian, if you could go back, I think actually, when you go back to the bit where you show how the column array is defined. Here. So I think Zhuzha's right, because if you change, so if you did the eBWT especially, or you change the if you tagged the dollars and no, but I mean, if you'd done the eBWT instead of a BWT, so it would change the order of the suffixes. So I don't know how, but it would actually change by changing the order of the rows. it would shuffle the column array as well. It would shuffle everything. So now the thing that was presented this morning is optimizing the number of runs in the BWT. I have no idea how you'd sort the dollars to optimize the number of runs in the call array.
Yeah.
But maybe before Davide graduates, he could figure it out.
Yeah, so maybe you should contact him.
Wait, but Gonzalo has a comment about this.
I think it's the same algorithm, no? You have runs, and then within those you have different letters, and you try to rearrange them to maximize the length of the runs. Now, instead of the preceding symbol, you have the column number. I think you can apply the same algorithm, no?
Okay, so we're not trying to, Davide wasn't using some sort of structure that related to the fact that it was a BW, you were optimizing the BWT. It could be because the call array, especially if you switch to pangenomograph, that can be sort of arbitrary. Well, okay, you're just saying it. Yeah, it depends on the input multiple sequence alignment, but it doesn't care that that's what it is. So if you tagged it with a pangenome graph, those would be vertices you reach with the suffixes in the pangenome graph. So it's like, but the thing doesn't actually care what those are. But yeah, so maybe it did. I didn't pick up enough on the presentation this morning to say that it should just work.
I think it's exactly the same thing. Now you have the column numbers, and you can rearrange the suffixes because they are all equal, so that you maximize the runs of the column numbers now.
Okay, so maybe it's worth. Sure.
You trying
Maybe
to,
it's worthy to, yeah.
What? You're trying to the column numbers, by rearranging this, you're trying to you can't just rearrange the columns.
No,
So
you rearrange the suffixes that are equal in the sorted set of suffixes.
So what you're saying is you would like to permute the rows of the multiple sequence alignment.
No. Yeah, the rows in the BWT, exactly as you did to maximize the runs of the preceding symbol.
Okay, so I'm not sure. I'm not convinced, because I have the feeling that here this depends. There is a dependence between the different groups of, because these aren't suffixes. These are just substrings. So if you rearrange one group to minimize the number of runs, doesn't that influence another group somewhere else? Like you're looking for, so in this case, in this example, it was all ATs. And now what happens to all CTs? Maybe in the same string. You see what I mean? I'm not sure this is independent. Well, because in the Bentley et al. Algorithm, the important thing is that rearranging the interesting intervals are all independent of each other.
Because when you have suffixes, they are equal up to some point, and then they differ, and then you don't care anymore. So you can just focus on the individual.
Exactly, and that has no influence on the rest of the BWT. And here I'm not convinced.
But still, if he doesn't want to recover the strings, he just wants to find the BWT range. The fact that you are breaking the sequences, I mean, if you follow LF, you won't recover a single string because you have arranged it in different ways across the way. Still, a range resulting from a pattern search will still be the same, and you will rearrange things inside range that can result from searches, even if it doesn't lead to a consistent order of strings all across the BWT. Maybe it still works in the sense that you're not following an individual string trying to recover it, but you will only consider range resulting from searches. I'm not sure now. I'm not so sure now.
Not
Okay.
yet convinced. Let's see. Thank you, Adrian, for a very interesting talk. Obviously,
Thank
one
you.
that made us all understand enough to be able to think about it.
Thank you for your interesting suggestion.
One last question, or we move to the next speaker. So let's thank Adrian again. And the next speaker is Diego Ortego, and he will explain us his work about contextual pattern search on grammar-based self-indexes for highly repetitive text.
Y el del medio es el que no hay que apretar. No, son los tres. It doesn't work. Nice. So my name is Diego Ortego. I'm a student of my advisory professor Gonzalo Navarro in DSC in the University of Chile. This talk is going to be a bit more technical, just as Fernanda's was. This is because my topic, I'm researching it as part of my undergraduate program and as a master's student at the same time. So this first talk that I'm going to give it goes a bit more into the engineering stuff. It doesn't go too deep into the engineering stuff because of this is a more theoretical conference, but yeah, you can expect more technical things. And the main takeaway I want you to get is the core of the problem that I'm trying to solve, because I'm still coming up with new theoretical ways of improving the results, these early results. So the contents that I'm going to talk about, I'm going to be explaining them as we go. First is the importance of highly repetitive text, which we have been talking about all day, so I'm not going to repeat much of it, but it's still important to remember that it's different from classical approaches of compression. And that it's growing larger and larger, the amount of highly repetitive text that we have and then we have to handle and that we should be handling efficiently. Pattern searching is a very well-studied problem. This is exact pattern searching over indexes of highly repetitive text. But it has some special properties that Navarro himself called attention to in a paper a while back, which is that when you search for a pattern exactly in a highly repetitive text or a highly repetitive text collection, you will often find occurrences that occur in similar contexts. So, for example, if you're searching for a word in a highly repetitive collection of natural text, you will often find it in the same kind of paragraph. Yeah. So if you're trying to find specifically the different contexts in which this word can be found, you are producing extra information that you don't need. So this is the motivation for the contextual pattern search problem, in which you also give some integer to your query to try to find this. I mean, to try to filter this redundant information that you would find when searching for a term in a historic database, or we're trying to search for the distinct introns that surround an exon in a DNA sequence. The state of the solutions of this problem is there's not much work about it. I mean, the only work approaching it is Navarro's paper, which is built on top of the R index, which is a classic index, and it's a large index. And it's theoretically very fast. It hasn't been implemented yet. And it doubles the space requirement of the R index to solve these problems efficiently. So this is not the base case scenario. And the formal definition, as I said, is you have a pattern that you want to search. You have an integer. This integer parameterizes the amount of characters to the left and right of the pattern that you want to find unique occurrences for. So you care about the first occurrence for every possible context of length L to each side. Yeah? Feel free to raise your hand if you don't get any of my definitions. So now I'm going to talk about grammars as compressed, highly repetitive text. This should be familiar to all of you. So I'm going to go fast. These methods are context-free grammars that compress the text. The idea is that the context-free grammar produces only the input string after being processed. And it can be easily extended for gaining random access. And you can add pattern search, which is where I'm starting. This is my starting point. I already have a grammar that has pattern search, and it can do it practically very fast. And I'm going to be extending it for contextual search. This is an example of why grammars are so powerful when compressing highly repetitive text. This is a very simplified example, of course, but the idea is that you take substrings that repeat often in the text and you turn them into symbols, and then those symbols can be expanded back when you want to decompress the text. To gain random access, you can add. Wait a second. Let me just, I think this is not the last version of my slides. Okay, anyways. So if you want to gain random access with a compressed grammar, you add some extra information to each node that tells you the offset that it has in the text, as well as the size of the text that it produces when you expand it completely. When I have the latest slides, I will do a bit of an example. Now, how do you turn this into an index that lets you do exact pattern search? First, we are going to wait for the slides. I'm sorry, but I need the little drawings on my diagrams. One thing I can tell you that's important about this slide is that we are showing how we are not storing the complete text by compressing it as a grammar.
Yeah, okay, just while we're waiting, because I don't know, how deep into the biology have you gone? Because cool effect.
You mean about the introns and exons part?
Yeah, because no, this has actually come up in a discussion that I'm CC'd on, although I don't understand it. And it was actually a biologist asking Ben Langmead about, so the term that came up was flanking genomes. So they're looking for like mobile genetic elements and stuff like that. And then they are really interested in the stuff that occurs to the left and right.
Yes.
Okay, so this is actually because
Yes,
okay, I
it
was
is
wondering.
important. Yes.
Okay, I mean, I was wondering how much you are dealing with the biologists on this
No.
because
I am not in contact with a biologist yet.
Okay. Because
But I have talked to some at the faculty, and they have expressed some interest.
okay, because also they I should ask you about this. So I don't understand what they're talking about, but they both seem very excited about using some stuff we've been working on to though I think this is more specific. What they're talking about, I'm not sure if it would actually do this as well as this will do. I am more hopeful about this approach for what they're asking. But okay, I'm just okay. That was just to kill time.
You're going to have to readjust your hope as I go along.
Okay. I just thought I would since we're waiting for the slide.
But I'm interested to know how hopeful you
Well,
are.
I can put you in touch with Noel and Ben. And so Noel is the biologist, and Christina is involved. And good. Okay.
Thank you. Okay. So, as I already explained, the context-free grammar attempts to simplify, compress the text by searching for repeated appearances and turning them into symbols. It only saves the symbols. And as a simplified algorithm of how this works, you'll know, you parse the text with some parsing algorithm. There's tons of them. You divide it into phrases, and you replace the repeated phrases as symbols, and you go along until there's no more phrases to recognize or the index is small enough. An important thing about the compressed string, as I said a little bit ago, is that you only really save the symbols from the grammar in memory. Everything else can be searched for virtually. And there's three types of nodes that we care about. There's the first mentioned nodes, the second mentioned nodes, and the terminal nodes. Terminal nodes are technically a special case of the first mentioned nodes. First mentioned nodes are stored directly in memory and can be expanded directly, while second mentioned nodes are the secondary appearance of a first mentioned node, and they need to refer back to the first mention in order for us to get the expansion back. Yeah, we do this using bit vectors and a BWT. I don't know if a BWT. I will transform. Yes. So in order to get random access, we would want to have the offset of each node in the text and its size. This is really easy to store using a sparse bit vector that marks the boundaries of each phrase in the text. This practically for free gets us both values for each node. We only need to do a couple of operations, and it gives us access time in logarithmic time with respect to the size of the grammar in simplified terms. The fields that this grammar tree has in code, kind of as a structure, is a balanced parenthesis representation that allows us to jump in and out of the different nodes of the tree. This is a default in practice. The phrase delimiter marker by bit vector, which is this one that I just mentioned, and the rest of the structures are for mapping first mentioned nodes like this A and B to their secondary mentions and back, as well as to the rules that correspond to them. Yeah. So how do the indexes work? The index, in order to search an exact pattern, the first thing that you have to build is called a grid. The grid is a way to speed up finding occurrences of this pattern in first mentioned nodes, especially in first mentioned nodes, and specifically at the border between two first mentioned nodes. What you do, as explained here, is you find all the prefixes that end at the border of a phrase, all of the suffixes that start at the border of a phrase. You reverse the prefixes, you sort them, and you build this adjacency matrix that tells you from a prefix and a suffix, where do they meet back in the text. We especially want the node where they meet. The primary occurrences of a pattern then are the ones that can be found at the edge between two phrases. So you find them using this grid, and it's very fast if you find a way to cut your pattern efficiently. So in the worst case, you have to consider all possible cuts of P. So you cut it, you get the prefix, the suffix, and you do the binary search in the grid. And depending on the amount of cuts, it may take longer or shorter amount of time. Secondary occurrences are different. These are occurrences that happened in second mention nodes. And to get to them, you use the auxiliary structures that I showed previously to jump from the first mention node from a first mention node that has an occurrence within to its next second mentions. And then you climb the tree because the parent also contains this first occurrence, and you continue searching for the parent's second mentions and so on. We are going to do something very similar when we're looking for the contextual occurrences. Now, what is local consistency parsing, and what benefits does it have when we are talking about grammars? Local consistency, kind of in layman terms, is a kind of pattern that does not care about global properties of your text, of the string that you are parsing. They usually still care about the direction in which you're parsing, but they don't care about, say, the variance of the alphabet or other such properties. And they guarantee a sort of familiar structure to subtrees that produce the same string within the grammar. We can add to this locally consistent parsing, run length parsing. There's an index that does this with the two mechanisms, and it makes the index smaller, and it doesn't add that much complexity to exact pattern matching. This is an index done by Diego Diaz. So this is what I explained just now. If you have a substring that appears multiple times in the text and is produced and enveloped, you could say, by two different nodes, these nodes tend to appear and store similar subtrees. Using local consistency, you can reduce the amount of cuts that you make of the pattern that you're searching. Why? Because since the local consistency parsing doesn't care about global properties of the string, you can get the same phrases from the pattern as you do from the original text. And you can analyze these phrase boundaries more efficiently. This gets you from p squared plus the number of occurrences times log of the size of the grammar order search cost to a log p, which is significantly better in practice, at least in my experience. This is my planned research. So what I'm trying to do is build a classic grammar index and a locally consistent grammar index that solve the contextual pattern search efficiently, at least as fast or faster than an algorithm that searches for all occurrences and then filters out the repeated context. The implementation, since this is more of a technical work, will be in C++, and I'm going to offer it as a free software license. And we still expect the locally consistent grammar to outperform the classic grammar, mainly because we're still going to be searching for primary occurrences, as you will see. So my progress so far is mostly on the engineering side. so I'm not going to bore you too much with it. But I have already adapted a locally consistent grammar and mostly a classic grammar to solve the problem without a too efficient filter. And I have implemented a more advanced solution using Ramin-Karp cumulative hashes. But this more advanced solution could use some work still. So what am I doing? To find the different contexts in which a pattern appears, what we need to do is to climb the tree from its first mention and second mention nodes to find the first ancestor, the smallest ancestor that contains the pattern and its context. Yeah? We have the guarantee that if we find all of them, then we have all of our results and extra. So we have extra information here still. Why? Because although we have found in this diagram B, the node B and C, which both contain the pattern and the context that we care about, they still are maybe large enough that they contain both the repeated context and extra symbols. Yes, this is we still don't know the amortized time. This is part of the work that I have to do. And one of the solutions that we first tried was to compare the strings to each side of the pattern. This means decompressing them, and it's terribly slow, of course. We have to travel all around the tree. I'm going to just show you practically what that means. So in this example, since, say, I find that this B has a contextual occurrence that I care about, if I want to compare those characters, I have to jump back to its first occurrence to retrieve the terminus that I want to compare. So there's a lot of jumping around. This is why this first solution is really not practical. I mean, you're going to see it in a graph in a bit. This first solution, the string comparison solution. The Ramin-Karp comparison solution is much more efficient, but it's still not as efficient as we would like it to be. Why? Firstly, because I'm not yet making use of a kind of recent, well, it's not that recent, but a paper that calculates the fingerprints of compressed strings in time proportional to the height of the tree. So for now, I am calculating most of the Ramin-Karp signature, but then I still have to check some indexes, some characters one by one in order to calculate the full Ramin-Karp signature of the context and the pattern. The preliminary results that I have, this is not a very formal graph, as you can see. There's not been much testing yet, but it serves for an important point that I will make later. The grep on the original text is a simple grep one-liner that you can do that finds all the contextual occurrences and filters them properly. The Ramin-Karp filter is the one that I just explained along with the character filter. And these other two are really interesting. Just search finds all the contextual occurrences plus the repeated ones. So there is no filter. We're getting extra results, right? So the problem statement is we want the first one for each unique occurrence. Here we're getting the first one and maybe the third one and maybe the fifth one. We don't know. We get the first one, so we have all results that we care about, but we have extra results. And it's the filtering that is so expensive. So finding out exactly what we want is the limiting factor for the speed of this problem. So you can see even the Ramin-Karp filter takes a lot longer than just presenting extra information. And of course, if we just search and then retrieve parts of the text and then do the filter, it takes even longer. So this is my brainstorming part of the of the presentation, there's still a lot of routes that I could take to keep on with this research. Some of the interesting ones, just interesting, there's more interesting ones later, is to, of course, implement the Bill et al.'s Raven-Karp optimization that I mentioned a bit ago. This should allow me to, it will allow me to not go around searching for terminal symbols within the tree, which is the most expensive part. There's also a suggestion that Diego Diaz gave me, which is to compress the suffixes and prefixes that are repeated between phrases. This speeds up the algorithm in the sense that if, when I go around looking for this smallest node that contains the pattern and its context, I can rule them out depending of, I can be certain that some of them are unique because I haven't compressed either their suffix if they're to the left or their prefix if they are to the right, right? If the suffix of the node to the left is not compressed, then I know then that its contents are unique. Therefore, this must be one of the contexts that I'm looking for. The really interesting routes that we could take are have to do with the traveling around in the tree. So, as I showed earlier, I'm going to just go back to here. We have to do a lot of jumping around still, right? We're still visiting the nodes that we may filter later. Ideally, we want to not visit them at all. Why filter if we only visit the nodes that we really care about, right? So instead of just jumping from secondary occurrence to secondary occurrence in order that they appear in the text, we might want to sort them by in this case, the suffix that starts to the right of this secondary occurrence, right? If they're sorted alphabetically, and we also store information on which is the longest common prefix that they have between each other, then we can skip a lot of results that don't matter. We can skip all of the occurrences that have a prefix that is in common with the last one, that is bigger than the amount of characters that we're searching for. An extension of this idea is to interweave the prefixes to the left and the suffixes to the right, character by character. This is something that I thought about yesterday, I think. It's not very practical thinking about it now. We discussed it with Navarro a little bit ago. Because if you see in this graph, if you start from this A, say, this A is the smallest node that contains this particular occurrence, and it may contain some of the context to the left and right. In this case, there's only 2 characters to the left and only 2 characters to the right. So this method of interweaving would work perfectly, right? We get to visit each next occurrence of A in order by their lexicographical, they're lexicographically separated to both sides, ordered by both sides. But if there was an extra character here, then this string that we are basing our sort on doesn't really work for us anymore. Yeah, because we have to compare the first character to the prefix on the left to the last character that is actually in my node, and then the second character to the left and the first to the right. We have to jump around. So this becomes much harder to accelerate. So the last idea that we have, which is not here on the slides yet, is to use a structure that is similar to the grid. Now the grid serves a very similar purpose. It finds adjacency points between different prefixes and suffixes, and each point, in here we are searching for rectangles that contain pointers to the ranges that we want. but each of these points is the adjacency between two different prefixes and suffixes, right? So if for each secondary occurrence we have a grid, or if for each secondary occurrence we have a grid, then we can find this unique adjacency between the prefix to its left and the suffix to its right. This seems like it would use a lot of memory, but we have to remember that there's only the amount of points is proportional to the amount of nodes in the graph at the end. And this has been my talk. These are my sponsors. Anid, thank you for taking me here. And DCC for paying for my bus. And thank you, Navarro, as well for all of his work as my advisory teacher. Yeah. As I said, the less technical part of this is just starting, so I'm taking in any ideas that anyone has.
Okay,
and
one really fast question. Travis?
Oh, Carlos has one. Mine are not fast.
Yeah, it's a very naive question. Is like, in terms of implementation, how are you going to measure if two contexts are, how different they are? Like,
all I care about is if they are different.
but like, just you care about equal differences, like just not equal, or
Yes.
okay.
It's not an approximate context.
Okay, and
yeah.
so it's not language based or anything like that.
No.
Okay.
Is there time for my no? Okay, I can take it. Okay, during lunch.
Okay.
Okay, so let's thank the speaker again.
Thank you.
And we are moving to the next talk, which is parameterized linear time string matching to DAGs, funnels, and beyond, given by Manuel Cáceres online. Can you hear me, Manuel? Yeah.
Can you hear me now?
Yes, I can.
Okay. I'll check my screen.
Okay. Okay, we can see your slides. You can start.
Okay, thank you. Okay, hi everyone. My name is Manuel Cáceres. I'm a PhD student in University of Helsinki, and today I will be talking about string matching in label graphs. So the input here is a directed graph, as the one shown in the picture. Sorry for the figures that I made by hand. But we also have labels on the vertices that we take from discrete universe called sigma or alphabet. And there is another input, which is a string from the same alphabet. We will say that the length of the string for this talk will be m. The problem is to find if there is a match of the string in the graph, in the label graph, meaning that we can find a path in the graph such that it spells the same string as the one that we are querying in the pattern. The string is called the pattern here. So why study this problem? There is an increasing popularity in label graphs in many areas, but more than everything is a fundamental primitive to locate information in label graphs in particular. So it should be solved. So for the state of the art in terms of algorithms, this was solved in time quadratic. And here when I say quadratic, it means the size of the string, the query string times the size of the graph, in this case, the number of edges, by Amir et al. By a simple and elegant idea they duplicate the vertices in layers and then connect layers in between. And the connections are made so that they replicate the connections in the graph, but at the same time, each layer represents some matching of a prefix of this pattern. And then the connection is only made if the edge exists in the graph, but also if the corresponding character matches with the label of that vertex. Actually, this algorithm was later used to solve approximate string matching level graphs in the same running time, the same idea. Now for lower bounds, Equi et al. Showed that this problem cannot be solved in better than quadratic time in strongly sense, meaning that you cannot reduce the polynomial or neither of the length of the string nor the number of edges under the strong exponential time hypothesis. And even when the graph doesn't have directed cycles, and it actually only has vertices like this, which are vertices with in degree at most 1, or degree exactly 2, or in degree exactly 2 and not degree at most 1. And in a later work that even showed that even if you allow polynomial time indexing, you cannot break that barrier. However, quadratic running time is still slow for such a basic primitive on these big data sets, for example, in bioinformatics. So is this the end of the story of the problem, this matching lower and upper bound for the algorithm? Of course not, because there are efficient heuristics solving the even harder problems like alignment, for example, in practice, which is a version of approximate pattern matching. So what can we do in theory? And what I'll be talking about in this talk is about efficiently solve the problem when restricting the input space, like the input for which we can answer that problem. And also, as a secondary objective, provide efficient algorithm to identify such input classes. So there are, of course, examples of this in the literature already. For example, in the paper of Equi et al., where they show the lower bound, they actually show that in the remaining cases of the classes of graphs, which are out-trees connected by the root by cycles, by a cycle, then they can solve the problem in linear time by an extension of Knuth-Morris-Pratt. Another example is a recent work by Rizzo et al. That show how to solve the problem in linear time in the size of the label direct product, which is just a refinement of this idea of Amir et al. And also, there is the idea of the generalization of Wheeler graphs or p-sortable graphs, where the problem can be solved in almost linear time, but it's hard to recognize whether a graph is p-sortable or not for some p. It's actually NP hard. However, recent advances on this have that drop, for example, the anti-symmetry from this sortability condition, can recognize this p in quadratic time in the size of the graph, which is still not good, for example, for bioinformatics, but it's much better than NP-hard. And actually, in this talk, if you restrict even more the problem to be a graph which is deterministic, like a DFA, you can also solve it in better than quadratic, which is a talk that you will have the privilege to hear after lunch, I think. So to see even more examples of this, like way to attack the problem in theory, let's take a detour to the history of the problem. So this started with the simplest case, which is just when the graph is a path, which is equivalent to string matching between two strings, like just a pattern and a text. And for example, you can use Knuth-Morris-Pratt like algorithms that pre-compute a function on the pattern and then traverse the text, in this case the path, computing at each position of the text the longest prefix match of the pattern with a path ending at that position. So just to remind you, I put the definition here of the failure function, which is for every prefix of the pattern. They compute the length of the longest proper suffix that is also a prefix of itself, which is also called a border. And this function can be computed in linear time for every value for every prefix can be computed in linear time in the size of the pattern. And I also put here this function, the failure function, as its string representation, and also an example. So for example, here, the prefix 8, prefix number 8, has the longest borders being 3, which means that there is an edge from 8 to 3 in this tree, which I will call the failure tree. But for example, 1 is also a border. And I wanted to show this here because of the relation between one prefix being the order of the other and its representation in this tree being one ancestor of the other, which is a concept I will use later. So you can use the failure tree, and you can also use, for example, the matching automaton that I call here, that you compute even more information. So for every character in the alphabet and for every position, then you can compute this table that I won't go into detail. But the thing with this table is that you can know the longest prefix match of the next character in constant time just by looking at one entry in this table. So to continue in this path, now going back to graphs, if you consider the graph being an out tree, which is just a tree, which it has vertices that are forking all the time, the same idea actually works. And you can store, for example, in the vertices of the tree, the longest prefix match that you have until that vertex from the root. And this idea can be extended even further to directed acyclic graphs, where if you consider a topological order of the vertices and you process the vertices in that topological order meaning that once you are processing a vertex, you can consider that all the neighbors have been processed already. Then you can just work in time proportional to the length of the pattern per every edge to compute the prefix matches of the current vertex. So you do this for every in neighbor, meaning for every in edge, and you take all the prefix matches of that vertex. You, for example, apply the automaton on those, and then you have the prefix matches of the new vertex. And you do this for all in neighbors, and then you, for example, can merge them, the solutions. And this works in M per edge, which then gives again the quadratic running time for directly acyclic graphs in general. So our contributions consist in showing how to process a vertex in this same algorithm, in this directed acyclic graph, in time that is parameterized, but a concept that I call prefix incomparable matches instead of order M per edge. And then use this parameterized algorithm to obtain a parameterization on the topology of the graph by at the same time generalizing out trees, in trees, and funnels. And I will also talk about what all of those are. And then provide efficient algorithms at the same time to recognize those graphs, those classes of graphs, that generalization. So we'll start talking about prefix incomparable matches. So here again, there is the failure tree that we were talking about before. So I say that two prefixes are prefix incomparable if one is not a border of the other. So in this, in the failure tree, it means that one is not ancestor of the other. Just that. For example, 2 and 3, which are here in different parts, are a prefix incomparable. And in the same way, I define a set to be prefix incomparable if every pair of prefixes are prefix incomparables. And here I define things, two important things or sets that are important for the algorithm now. So B sub B is the set of prefix matches with paths ending at B. This is the same set that the algorithm by Park and Kim use this set. But now we have this secondary notion of the same set, but of prefixing comparable vertices. The idea here is that Pi of B, now that vertex, is the unique prefixing comparable set representing B of B. So for example, if all the vertices that match until the vertex B are 0, 1, 2, 3, and 8, 0, 1, 2, 3, and 8, so all of those, including 0, then the prefixing comparable set is just 2 and 8. And you can see that, in a sense, these are the lower level prefixes, such that as ancestor, they incorporate all the others, in a sense. So what I show is that we can compute the prefixing comparable set for a vertex, the one representing all the matches in a vertex, from the prefixing comparable sets of the in neighbors in time that is parameterized by this quantity, which is just the sum of the size of the prefixing comparable neighbor sizes, which I call K sub B, and then square. And I can do this in after m processing time. I will tell you a little about how I do this. So I just use this idea of being ancestor of each other for being prefixing comparable. So for example, I can compute lowest common ancestor queries on the suffix tree in linear time, preprocessing time. And then noting this that I've been saying a lot of times now, then I can, for example, concatenate all the in neighbors prefixing comparables into a list, then use the matching automaton to obtain the corresponding ones for B. And finally, remove the prefix comparables there by just doing, like, comparing all against all, which is quadratic in the number of this sum. And that's why it's K squared, KB squared. So this is already parameterization, but I could do better. So if you represent the failure tree, for example, the valence parental representation of this failure tree, then you can do it actually in time proportional to sorting this KB after m preprocessing time. And you can do can go even further by using the suffix tree of the reverse of the pattern. And then you can do it the same, computing the prefixing comparable matches in linear time in this KB. So now I will go into out trees, in trees, and funnels, and how we can generalize them. So an out tree is just a normal tree, such that the vertices are forking. Here is an optional definition. An in tree is the same, but now the vertices are like merging until a root. And a funnel is like a combination of both, in the sense that it's a graph such that you can partition the vertices into an out tree, an in tree, edges going from the out tree to the in tree, but not in the other direction. So this is a funnel. And we present 3 different linear time algorithms to recognize funnels. And actually one of them outputs the partition into S and T. So for the generalizations that I call classes SK, TK, and STK, we say that a DAG belongs to this class. For example, SK is the number of source to V paths is at most K, and I will use this notation for referring to source to V paths, number of source to V paths. So for an out tree, this will be 1, this K. This is the analogous for an in tree, where also K will be 1. So the number of vertex to sync paths is at most K. And for an STK, we will see that it belongs to this class if the number of, if one of these 2 conditions holds for every vertex, like either the number of source to vertex paths is at most K, or the number of vertex to sync paths is a most k. And we also generalize the three recognition algorithms I mentioned before, including this one, this lemma, which is a very similar characterization as the one of funnels. So we can recognize, we can find actually in linear time, the partition, a partition in the vertices for a graph in STK. If a graph is in STK, then we can find in linear time a partition of the vertices such that one part is actually an SK and the other part is a TK. And there are no edges from V2 to V1. There are no edges in the other direction. So the analogous definition to funnels, but now generalized with this parameter K. And moreover, if such partition of the graph exists, then you can conclude that the graph is an STK. So now there are some very simple observations, which is just that saying, for example, that the number of prefix incomparable matches that you have until one vertex is at most the number of source to vertex paths, which is at most k if you are SK, for example. And this is a lemma proof. And then you, by also noting that if S has a match in a graph, then the reverse of the pattern has a match in the reverse of the graph. It means that a graph being, and also that a graph being in SK is equivalent to the reverse being in TK. We can obtain parameterized algorithms for graph in SK and in TK also. And this theorem condenses this, so we can decide whether the pattern has a match in the graph in time proportional to the size of the graph times the scale plus the time for building the automaton, where this k is actually the minimum between two maximums, so whatever is better, the maximum between the source to vertex paths or vertex to sinks path. And actually these numbers, these maximums, are the minimum values for which the graph can be SK or TK. Those are the minimums K. So to solve the problem in STK now, we first find the partition into SK and TK. And now we know how to solve the problem in SK and TK separately, so we can solve matches there independently. And then we need to solve the matches crossing from S to T from the out tree to the in tree, for example. And to do this, we show this lemma that we can decide if there is a match from the pattern using an edge in some time after m squared per processing time. And the time that it takes to figure out whether there is a match or not is proportional to the product between the number of prefix incomparable matches in one of the parts to the number of suffix incomparable matches in the other part, which is just applying the same algorithm, but in the reverse graph. This can be done by filling up this dynamic programming table, whose size is m squared. And that uses the failure function of the pattern and also of the reverse. And what this table answers is just whether there is a way to, whether there exists a period of this prefix and a period of this suffix such that they add up to exactly m. So then you can find a match using that edge. It's just that. And then with this, we can decide whether the string has a matching in the graph in time which is proportional to the size of the graph times k squared because of the prefix times suffix, plus this m squared for pre-processing this table. And now the k, the parameter is a bit better, is instead of the minimum of the maximum, it's the maximum among the minimums of the two quantities. And actually this k is the minimum value for which the graph is an STK. And we can say that this algorithm is linear parameterized by k, for constant k, but it still it's not linear in general. It's quadratic in the pattern because of the pre-processing time of this table. So the open problems are whether we can do better than this k squared plus m squared for SDKs, or even for funnels. Like, can we do better than m squared for funnels? And I received this comment from a reviewer that you can actually do it in k squared log m plus linear in m. But here you sacrifice being linear in the graph, because now you are multiplying the graph times the logarithm of the pattern. But anyway, it's much better than just multiplying by the pattern itself, which is a very good idea. And it's based on string periodicity, but I haven't read it yet, so I'm not sure if it is correct or not. I believe the reviewer. Whether this technique can be extended to counting matches or reporting matches, or whether this string can be extended to now graphs that are string label graphs. Not that the vertex have just character, but strings. And then you don't want to do the old trick of just decompressing the string into a unitary path and then apply the same algorithm, but you want to sort of work in time proportional to the original graph, and then maybe plus the total size of the strings contained as vertex labels. Also, there is this open how this behaves in practice, and whether or not these techniques can be generalized to cyclic graphs. I would like to end by acknowledging who support me and my group in Finland, and I'm be happy to take questions now.
Thank you, Manuel. Any questions?
So first, I'm hoping Nicola Catumacho is online in case he has a question.
I think he's next.
Oh, he's next. Do we get it right?
I am online.
Okay, so I'm surprised Nicola isn't asking. So I handed over. But have you seen Nicola's stuff on quotient graphs from DCC this year? Maybe that was.
Yeah.
Okay.
I think it's actually this one that I mentioned here.
Oh, so that was the 10. So piso. Oh, okay. Oh, so 10. That was the quotient. Okay.
Yeah,
so
the
I should actually hand it over to Nicola. Okay. So Nicola, do you have a question?
No, I have a very blurred question, very generic question. The last thing that you mentioned, I mean, which kind of problems do you expect when trying to generalize this to cyclic graph? I mean, I understand that it's much more difficult because you have infinite paths reaching every vertex. So, I mean,
yeah,
your structure doesn't directly work, but I mean, at least graph where, I mean, there are some notions of, how can I say, some notion somehow capturing the idea of cycles included inside other cycles. So what I want to say is that at least for a graph where you don't have difficult cycles, let's say that you just have easy cycles in some sense, let's say, do you think that these ideas can be generalized?
And I think so. Like, I mean, and this algorithm that these guys like Massimo and Ecuador, they chose how to solve the problem in this realm where you have a cycle here actually, and then you have trees. And what they do is just to like execute the node more spread along the cycle. You don't have to execute it that many times, and then you can go to the tree. But it depends on the topology, of course. Maybe you are thinking of something more complicated than this.
Okay.
This is actually not more spread too. This algorithm.
So let's thank Manuel again.
Thanks.
And we are moving to the last talk of this session, which is Finding Memes on Wheeler Graphs by Nicola Cotumaccio. So Nicola, can you share your screen?
1 second. Okay. Can you see my screen?
Yes, I can see it very small.
It's small?
Yeah, quite small.
Oh, why?
The slides.
Wait, let me try to share the whole screen, maybe. Wait. Entire screen. Now?
Now, yeah. Yeah.
Okay.
So can you start?
Okay, so since this is a workshop where we are somehow supposed to talk about changing results, I guess, I'm going actually to talk about a slight variation of MEMS problem, which is the matching statistics problem. Actually, the matching statistics problem can be probably considered as a more general problem as compared to the MEMS problem. And matching statistics have been introduced because often in application, but also from a theoretical point of view, one is not interested in finding exact matches, but just approximate matches when solving the pattern matching problem. And so what are matching statistics? Let T be my reference string, and let pi be a pattern that I want to match against T. And finding matching statistics essentially means determining these numbers. What are these numbers? Well, L1 refers to the position 1 of my pi, so which shall start with S. And what I want to understand is what is the longest string starting at position 1 that also occurs in T. So, for example, the character S occurs here, for example, but the string ST does not occur anywhere. So this means that the longest string starting position S occurring T is the one or length 1. Then I move to position 2, and I wonder the same. What is the longest string starting position 2 that also occurs in T? Well, actually, the character T does not occur in my reference string. So the longest string is just the empty string. And so that's why L2 is equal to 0. Then I move to position 3, and I wonder the same. What is the longest string starting position P that occurs in T? Well, character P occurs here. String PI occurs, for example, here. And string PIS doesn't occur anywhere. So this means that the longest such string is the one or length 2 PI, and so on for all positions. So we have 7 values because the length of pi is 7. And these are just the same values that I displayed in the previous slide, but now I'm also adding for each such longer string the interval corresponding to the string that I managed to found in the set of all sorted suffixes on my reference string. So what I want to say is that consider position 1. We said that the longest string starting position 1 is just character S. And if I consider the sorted suffixes of my reference string T, well, all the suffixes starting with character S are the ones in position 9, 10, 11, and 12. So the corresponding interval is N12. Or for example, consider position 3. We said that the longest string starting at position P and occurring T is PI. And actually PI in the sorted list only occurs at position 7. So the corresponding interval is just 7, 7. And why am I doing this? Because okay, matching statistics problem is a problem that can be solved using a suffix tree, but over the years, the research developed in such a way that since suffix tree has space problem, it takes too much time to store a suffix tree. The various components of suffix trees have been compressed. And so around in 2010, Inspire, it was proposed an algorithm to compute matching statistics that relies on compressed data structures. And these intervals play an important role because these intervals can be essentially seen as the interval in the standard backward search. And so the algorithm to compute this quantity actually relies on the backward search plus one component of a suffix tree, of a compressed suffix tree, that is the longest common prefix array. And so the idea of the algorithm is as follows. Start now from the end of the string. So start from position 7. Well, the first thing that I do is just to apply a step of the backward search starting from the whole interval 1, 12 and character I. So if I apply a step of the backward search, well, the backward search just returns the intervals of all occurrences of character I. And so it returns the interval 2, 5. And so this means in particular that the longer string starting in position 7 is the one of length 1 because it's the last position. So the longest string is either the empty string or it is the one of length 1. Then I apply the backward search again, starting from interval 2, 5 with character S and obtain interval 9, 10. So this means that 9, 10 refers to the suffixes starting with SI. Then I apply backward search again, starting from 9, 10 and character S and obtain 11, 12, which means that actually SSI is 11, 12 is the interval corresponding to suffixes starting with SSI. Now I try to apply backward search again. So starting from 11, 12 and character P, so I should obtain the number of suffixes starting with PISSI. But as you can see here, there is no suffixes starting with PISSI. So this means that the backward search returns the empty set. So this means that we somehow have to find a way to understand what is the longest prefix of PISSI that occurs among this list. And we already saw that this prefix is actually going to be PI. So it's going to be, yes, it's PI and so corresponded to the 7th string. And so how can we do this? Well, let's go back to ISSI here. Well, if I pick the prefix ISS, the number of suffixes starting with ISSI is 2, and the number of suffixes starting with ISS is still 2. So this means that if I try to apply the backward search starting from this from the interval corresponding to ISS, well, this interval is still going to be 4, 5. And so when I apply the backward search, I'm still going to get the empty set. And the same holds true for suffixing starting with IS, because still the number of suffixes starting with IS is just 2. But if I consider the number of suffixes starting with I, well, the number of such suffixes is more than 2 because it's 1, 2, 3, 4. So I may try to apply the backward search again. And now there is some hope that the backward search returns the empty set. And indeed, when I apply the backward search starting from I and character P, now I don't obtain the empty set, but I obtain the interval 7, 7, which correspond to a suffix starting with PI. And then I can go on with my algorithm. So in order to apply this algorithm, I basically I need a way to solve 2 sub-problems. The first sub-problem is to understand how to determine the longest prefix of a string such that the number of suffixes starting with that string, with that prefix, is larger. In this case, we in our example, we knew ISSI, which is associated with interval 4, 5, and we needed to determine I, which is associated with interval from 2 to 5. And the second problem is, given the interval 4, 5, we must find a way to determine the interval 2, 5, so that we can then apply the backward search starting from 2, 5. The first problem is solved by means of the longest common prefix array, which simply stores the length on the longest common prefix between one suffix and the previous suffix in this sorted list. So for example, here, this value is 1 because the longest common prefix between this string and this string is just I, which is length 1. Or for example, this value is equal to 4 because the longest common prefix between this string and this string is ISSI, which has length 4. So by using this data structure, we can actually solve the first problem. That is, we can easily determine that the longest prefix, which allows us to make the interval larger, is actually the one of length 1, which is I. And then in order to determine the interval 2, 5, well, we can use some queries, which are called next smaller value queries and previous smaller value queries. So essentially what we have to do is to, starting from the values associated in the LSP array 2, 4, 5, which is 1, 4, we must move along the LSP array until we meet a 0. And so when we meet a 0, we actually meet the border of our intervals 2, 5. This is the intuition. So this algorithm has a number of iterations linear in the length. It can be easily checked that the number of iteration is linear in the length of pi. Now, 5 years ago, Wheeler graphs were introduced. I'm not going to give the definition of Wheeler graph, but the idea is that Wheeler graph generalized this idea of suffix sorting. So consider state tree and consider all strings that can be read starting from tree and by following edges in a backward fashion. Here we assume that the initial state, this is just a technical assumption, has a self loop labeled with hash. So this means that the strings that I can, essentially this technical assumption corresponds to the idea of the termination character $ in a string. And so the string that I can read starting from tree and going backward are going to be A, B, D, G, hash, 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 are going to be A, B, E, H, hash, hash, A, C, E, I, hash, hash, and so on. Notice that this set may be also infinite because here, for example, we have a self loop. So the set of strings that I can read starting from here are infinite because I can stay on this state an arbitrary number of times and then I can go backward. Maybe I can go backward. I can also stay here forever. And in particular, we can define a shorter string entering a state and a larger string entering a state. So for example, shortened and largest, I refer to lexicographic order. So the shortest string that I can read starting from 2 is going to be A forever. And the largest one is going to be A, B, D, F. Because, for example, another string that I can read starting from 2 is going to be A, B, D, F. And you can see that the string A, B, D, F is lexicographically laced between this string and this string. And it can be shown that, okay, it's pretty obviously the smallest string that I can read is smaller than the largest string that I can read. Okay, that makes sense. But what one can actually show is that the largest string that I can read starting, say, from state 2 is smaller than the smallest string that I can read starting from state 3. So this means that the sequence of minima and maxima is sorted, is lexicographically sorted, and this leads to introduce a pretty natural generalization, the LCP array, which now contains 2n-1 values, not just n-1 values. And essentially, I just pick the length of the longest common prefixes between pairs of consecutive values here. So the longest common prefix of this and this, the longest common prefix on this, and so on. Now, as I told you, this Wheeler graph, Wheeler automata generalized the idea of suffix sorting, and in particular have the same functionalities that have shared by the FM index. So if I consider the set of all states reached by the string pi, well, this set is an interval with respect to an ordering of the states. Essentially, a Wheeler graph is a graph where there is an order of the set of states having some properties. And the order, here states are numbered according to this order. And for example, if I try to locate the occurrences of EC, well, if I follow Legis label E, I end up in 12, 13, 14, which is an interval. And then if starting from this set of states, I also try to read C so that I consider all states reached by EC. Well, EC, I end up in 8, 9, which is also an interval. And intuitively, this process that I describe now is a generalization of the backward search, which is now called the forward search because I'm following edges in a forward fashion. And so this leads to a pretty natural generalization of the matching statistics problem. And I'm not going to give details, but the intuition is that the LCP array can still be used to essentially apply a pretty natural generalization of the algorithm on strings that I described before. But now, solving the problem is a bit more difficult because we have a graph structure. And I give you just an intuition of why the problem is more difficult. Consider the string pi, the string pi, HEBA. Well, the only state that I can reach by reading this string on this automata is going to be 3, HEBA. There are no other paths that I can follow labeled HEBA. And if you remember the algorithm, at some point I needed to shorten my pattern. This happened when the backward search returned the empty set. Now it's going to happen when the forward search returns the empty set. So at some point in the algorithm, I may need to determine the longest suffix this time of pi, which occurs in the graph, which matches the graph. Well, and again, if you remember the algorithm, it's not enough. I must determine the longest suffix which matches the graph as such that I'm going to widen my interval. So in this case, what I have to do is to consider the longest suffix such that the number of states reached by this longest suffix is going to be larger than 1. So HEBA only reaches state 3. The suffix EBA only reaches state 3 again, so it's not going to work. But the suffix BA, well, it still reaches state 3, but it also reaches state 2. So this means that the suffix, our desired suffix, is going to be BA. But the problem is, can we determine that the longest suffix is going to be this one by only using the LCP array? And the problem is that we cannot. The reason why we cannot is that the LCP array only stores the distance between the maximum string reaching 2 and the minimum string reaching 3, and the maximum string reaching 3 and the minimum string reaching 4. But the maximum string reaching 2 is going to be A, B, D, F, and so on, and the minimum string reaching 3 is going to be A, B, D, G. So the longest common prefix is going to be A, B, D, which has length 3. And similarly, the longest string reaching A, C, E, and the minimum string is going to, sorry, the longest string reaching 3 is going to be A, C, E, I. And the minimum string, the only string actually reaching set 4 is going to be A, C, E. So the longest common prefix is going to be A, C, E, which has length 3. So this would imply that the minimum, our desired pi prime should be the one of length 3, but we saw that it is actually the one of length 2. And why do we have this problem? Well, because even if there is some string labeled HEBA reaching state 3, this doesn't mean that all string reaching state 3 are labeled with this, and in particular, the minimum string, the maximum string need not be to be labeled with HEBA. So remember here, the minimum string is going to be this one. Well, the label is not going to be HEBA, but the shared part is only going to be BA, the one of length 2. And similarly, the longest string, we consider the maximum string reaching state 3. Well, we don't have an occurrence of HEBA, but the longest shared part between this string and HEBA is only going to be A, because then here we have a C and not a B. So it's only going to be the one of length 1. And so this 2 is the one implying that the desired suffix is the one of length 2. The problem is that these values are not stored in the LCP array, in the generalized LCP array, because they depend on how our string pi, which is given at runtime. So it's not, we cannot pre-process pi. I cannot explain the solution, but I will just give an intuition. The intuition is that we must keep track value of these values as pi is updated, as pi changes. And the difficult part is to show that when our string changes during the algorithm, we can actually update this value on the fly. This is doable, but I mean, this is too technical to be explained in this talk. Okay, thank you very much.
Any questions? One fast question. No, no questions.
I have a.
Okay, Manuel.
I have a very quick question because we are running out of time for lunch.
Is Manuel raising his hand in the chat?
Oh, sorry. Right, Manuel.
Hi. Okay. So you talk about deterministic Wheeler graph. So why not non-deterministic, or is it more difficult in general, or why?
Yes, the problem. I'm working on it, and I'm basically sure that it can also be generalized to non-deterministic Wheeler graph. But things become, and also it can be generalized in an efficient way. But things become more complicated, and intuitively, the reason why they become complicated is because this change on inequality is no longer true. Because if we have a non-deterministic graph, it may happen that there is some overlapping between the string reaching the same state. And so in particular, it's no longer true that the maximum string starting from here is going to be smaller than the minimum string starting from here. Just think of the case where a state is reached by several strings. You have two states reached by exactly the same strings. Well, in this case, it's no longer true that the maximum of the one that you dub to be the smallest one is going to be smaller than the minimum on the other one. But I still think that this difficulty can be overcome by taking care very carefully of the algorithm, because essentially here the algorithm relies on is just suffix sorting. So as long as we can perform starts the idea of the backward search or the FM index, it's clear that things are still doable. They just become more technically complex, but I'm pretty sure that it can still be done. This was just, I mean, an easiest way to introduce the ideas that one need to take into account when generalize the problem from strings to graph.
And what about p-sortable?
Okay, I'm pretty sure that I'm pretty sure that you can do this with p-sortable. I mean, as long as you do this with a graph, yes, it's pretty. I mean, you just define a PLSP arrays. Yes, I don't expect any particular problem for generalizing this to p-sortable graphs. Yes.
Okay, thanks.
You're welcome.
Adrian? Adrian?
Now can you hear me?
Yeah, now yeah, we can hear you. Are we going to lunch?
Yes, we are going to lunch and we will be here 2:30. Okay, and we try to keep the schedule.
to compare some AB to the omega. Omega means infinite copy of this. So comparing these two strings, infinite copy of two strings, can be done by comparing their length L prefix, where L is less than the sum of their lengths. So actually, we can extend the suffixes up to order of n. So required length is order of n, and we double at each iteration. So the number of iterations is order of log n. So the time complexity will be order of n scaled of n. And for a cyclic case, it is actually a similar idea used in the sorting algorithm for a cyclic Wheeler DFA. So we sort the nodes topologically. Then when each node is input topological order. So when a node arrives, then we know that the order of its predecessors. Then we can actually compute the new node, the order of new node using their minimum or maximum predecessors. So when a node is arriving, then we can actually using the predecessors, and for minimum string, we take the minimum one, and actually we do this as something like a dynamic BWT construction. So each operation on this dynamic structure takes a log n time, and for each incoming node, we need a constant number of operations, so time complexity will be order of m log n. Yes, it is the end of my talk. I have addressed some problem of sorting of DFA lexicographically, and I have presented two algorithms. And future work will be some improvement of our algorithm, especially for suffix doubling algorithm. And this is the acknowledgement. Thank you for listening.
Thank you very much, Sungwon, for the talk. A really interesting topic. We have some times for questions. Are there any questions from the audience?
Seems to know. Can you hear me? Yep.
The auditorium is muted, so we cannot hear them.
Can you hear me now?
Okay.
Max?
Yeah.
Can you hear me? Okay. There is
Yeah.
no questions, but I don't know if I lost something, but for me it wasn't no clear how they implement the predecessor. Which structure they are using for that.
Suffix doubling algorithms?
Okay.
Or which part? This part one?
I cannot see it now. I mean the pipeline between the nodes in the two graphs.
You see this screen?
No.
No. I'm sorry.
Is this the slide, Adrian?
What?
Is this a slide?
No, it's one when suddenly he changes the links, the predecessor links for other links. Those ones.
You mean this one?
No, the next one.
This one?
That one, I think. Yes.
This one? You mean this
the
one?
last one. I didn't understand where those links
yes.
came.
Yes. Okay. I will explain that. Now we have actually sorted using the length 2 suffixes, right? But the predecessor is the length 1. So if we want to get the length 2 predecessors, we can actually follow the predecessors of the predecessor. Yes, so for node 5, we can actually, its predecessor is node 4, and predecessor of predecessor is node 1. So we can actually follow this link twice, then we can actually update the predecessors as node 1 for node 5.
It's like 2 steps of predecessor, no? Always.
Yes.
Oh, okay.
Yes, actually, more precisely, actually, we concatenate all the predecessors of the predecessor. Yes. Because we can have a multiple number of predecessors, and also the predecessors also each of predecessor has a multiple number of predecessors. Actually, we can something like a two-hop graph. We actually collect the two-hop nodes.
Okay. So thank you.
Thank you.
We have here another question, Max.
Okay.
Hi. If you wanted to do regular expression searching on the graph, could you do the same process on the automaton of your regular expression and the automaton of the graph and somehow intersect the intervals, see which intervals intersect, and those would be the solutions that works?
Yes, actually, the regular expressions can be represented as a DFA. So we can actually index it DFA, but if the regular expression is so complex, then maybe we need so many partitions here. Actually, it is out of the topic of this work, but that's very good question, because if the order of width is actually critical to the searching time, and also it affects to the space complexity. Yes.
So it will be the product of the width, and for each path you will have
as
to
far
do
as I
MERS,
know,
yeah.
for time complexity, p squared time will be p squared will be multiplied.
Yeah.
Yes, so in the worst case, maybe we need quadratic time for searching something.
Yeah. Okay.
Okay. I think we are on time, so thanks again for the talk. And
thank you so much.
We can move to the next speaker. Okay. Okay. Next speaker is Francesco Sillo. And the screen is shared. So next speaker is Francesco Masillo, and he's going to talk about maintaining the cycle structure of permutation efficiently.
So, hi everyone. My name is Francesco Masillo, and I'm going to present you a new data structure for storing and updating permutations while maintaining some information about the cycle structure. And this is joint work with Yujian Nalik. So let us start by looking at this permutation and its cycle decomposition. For those who are not familiar with the cycle decomposition, one just has to follow the trajectory of the permutation to build these joint cycles. So in that case, starting from 0, we already mapped back to 0, so we have a cycle left 1 with only 0 in it. Let's say that we start from index 1, then we have to map to 2, then follow the mapping of 2 to 5, 5 to 7, 7 to 4, and then 4 maps back to 1, so we have a cycle of length 5, and so on and so forth. See now that we want to swap two elements of the permutation, say pi of 1 and pi of 7. Then this will also change the underlying cycle structure, because as you can see, now that we have swapped 2 with 4, 1 maps directly to 4, and 4 closes already the cycle, leaving to 2 disjoint cycle instead of a single one. So now that we want to swap another 2 elements, this time power 4 and power 9, and again we have changing the cycle structure, but this time we have joined the 2 cycles into a single one. Overall, when we want to apply a transposition to a permutation, we have 2 possible outcomes. So we either join 2 cycles into one or split 1 cycle in 2. This solely depends on whether the 2 elements that I'm transposing are originally in the same cycle or not. And with the standard representation of permutation, like the one-line representation stored in a simple array, keeping track of even just the number of cycles takes O(n) time after each update. So this is quite inefficient. That's why today I'm going to present you a new data structure called the forest of split trees that built on the cycle decomposition can handle changes in the permutation in the form of transpositions efficiently. And as you can see, we have 1 split tree per cycle of the input permutation, but I'm going to elaborate more on that in the next slides. So this was first presented in a previous work by Giuliani et al. In TCS 2021, where we used the forest of split tree to accomplish 2 very specific operations on permutations. So we applied neighboring transpositions in the form of pi of I and pi of I plus 1. And we also knew that pi of I always contains 0. And then we wanted to return the number of cycles after each update. As you can see, these are very niche operations. And for that, today I'm going to present you an extended range of operations and also compare this new data structure with some other found in the literature. So let me start by introducing split trees. And they were first proposed by Slater and Tajan in 1985. And they are a special kind of binary search trees that are not necessarily balanced. And they have a peculiarity of granting quick access to recently accessed elements thanks to a subroutine called splaying, which I'll cover in next slide. They support basic operations in amortized O(n) time thanks to the rearrangement, dynamic rearrangement of the tree. And those operations are access, insert, and delete on single nodes and join split on distinct trees. So as promised, I covered the splaying operation, and basically after each access of a node or any operation on a node, we have to rearrange the structure of the split tree by moving up to the root the element x, thanks to the splaying subroutine. This splaying subroutine has 3 cases with some cute names, zig, 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 and zigzag. And so for the first case, we can apply it when the element x is a direct child of the root. As you can see, in this case, we have x that is to the left of its parent p that is already the root. Because we have to splay x, so bring x to the root, we are going to perform an edge rotation on the edge between x and p. And as you can see, the tree on the right has x at the root, and the relative orders of each subtree and p are maintained, so we don't break any constraint on the binary search tree. See now that x is further down the tree, and so it has a grandparent. Then we either choose a zigzag or a zigzag operation. So the former is when x is to the same side of its parent, and its parent is to the same side of the grandparent of x. In this case, we have x to the left of p and p to the left of g. This time we have to perform 2 subsequent edge rotations. The first has to be done on the edge between p and g, resulting in this middle tree. And then finally rotating the edge between x and p, bringing x to the root. Again, a correct shape of the tree. And the last case is a zigzag. As you can see, in this case, x and p are not on the same side, so x is to the right of p and p is to the left of g. We have to first rotate the edge between x and p, and then between x and g, resulting in this last split tree. And this splaying can be concatenated to bring x anywhere down the tree up to the root. So going back to our data structure, if we look at a specific cycle, let's say this one highlighted in red, you can see that there's something odd going on if we look at the numbers inside the node. So there's a 4 to the right of 5, and a 7 that is to the left of 4. And if this was a normal binary search tree, we would violate its properties. But we are not actually indexing the nodes by these red numbers, but by the blue numbers that are representing the relative position of the elements in their own cycles. So we have 1 in position 1, 2 in position 2, 5 in position 3, and so on and so forth. And so if we actually index the elements of this tree by these blue numbers, we have a correct binary search tree, that in this case is a splitter. So we represented the first split by means of a matrix with n columns and 3 rows, one for the parent node information, one for the left child and right child information, respectively. We also store a counter for the number of cycles, that in this case is equal to 4. And this representation grants us constant time access for each node in the first split trees. And then each operation on the permutation consists only in a constant number of split tree operations. Before covering the operations, I want to remind you that cycles are equivalent up to rotation, meaning that if we take again the same cycle as the previous slide, we can view the cycle as a circular string. So we can say shift 4 from the back of the cycle to the front, and this would be equal to the previous one. Of course, we can also update the underlying split tree, and the split tree would be equal to the one to the left. We can repeat this process for the length of the cycle, and this time maybe bringing 7 at the beginning, and so on and so forth, and these are all equal cycles. Now, if we want to do some queries, say we want to return pi of I, in the standard cycle notation, we would have to find I and then returning the next element in its own cycle. So say that we have found I, because of the way a cycle is built, by repeatedly applying the pi of I, you know that once we find the index I, we then have to return its immediate successor in the cycle. So this would translate in this first split tree to returning the leftmost node in the right subtree of I. So as you can see, we access I, then we go once to the right and then all to the left. And this corresponds to the correct answer because it's the immediate successor of I. And I remember you that if we do an order traversal of the tree, we actually get back our cycle. So this is the correct operation. Let's see an example. Say that we want to return pi of 2, that we can see that is equal to 5. So we find 2 and return the immediate successor in the cycle notation. Whereas in the split tree associated to the cycle, we have first to access 2 and splay it. So changing the shape of the tree to this following one. And then we go once to the right and then try to go all to the left as far as we can go. But in this case, we have to stop already at node 5. And so we splay it and return the correct element for the query. As I mentioned at the beginning, a very crucial query is the one asking whether two elements are in the same cycle. This is important when we want to transpose the elements afterward in order to know if we are splitting a cycle in two or joining two cycles into a single one. So in the cycle notation, we would have to access X and then traverse its cycle to check if Y is there. But as we anticipated, this is quite inefficient. Whereas in the first split trees, we just have to display X, then display Y, and check if X is apparent. If the answer is positive, then X and Y are in the same cycle. Intuitively, by concatenating display of X and display of Y, we first make X float up to the root, and so we are sure that for the time being it has no parent. Then, if we display Y, and they were actually in the same cycle, we would have to move X down in its own tree. So now when we check if X is a parent, and the answer is yes, we are sure that they are in the same cycle. Because they are just spring operations, this takes amortize all of them time. So another example, maybe we want to check if pi of 2 and pi of 10 are in the same cycle. As we can see in the cycle notation, we find 2, and then we traverse the whole cycle, and we don't find 10, so we know that they are into this cycle. In the split trees, in the process of split trees, we first display 2, then we display 10, and then we check if 2 has any apparent, and the answer is here is no. So we have successfully answered the same cycle query. Say that now we want to apply the transposition of pi of I and pi of j when this is a merge case, as I showed, because the two elements are in two distinct cycles. So in cycle representation, we have pi of I and pi of j in two cycles, and they are preceded and followed by some other elements that are represented by these colored rectangles. And because we are swapping what the element mapping to pi of I, on the right we see that pi of I now will map to the purple rectangle, and pi of j will have to map to the green oblique lines rectangle. In fact, on the right we see the blue rectangle with pi of I followed by the purple one, the orange, and then pi of j, and then pi of j is followed by the green rectangle. I want to remind you that because cycles are equal up to rotation, we can shift this green block at the beginning by maintaining all the others in the original sequence, and this is still a correct cycle. And this is useful just to visualize the outcome of the first split trees when updating it with a transposition. So in the first split trees, we have the same visualization, but this time with subtrees colored in the same manner. And so because we want to map now pi of I with this purple subtree, we have to make room for it. And so we do a cycle rotation of the trees, so that now we have pi of I that is the rightmost element in some tree. And we bring also the purple subtree on the left of its own tree. So that now we can just perform a simple join operation, linking pi of I, that is first displayed, and is now linked to this purple subtree. And as you can see, with another traversal of the joint tree, we have the same cycle as we can see on the top. As promised, I'm going to also compare the Poisson split trees with the other data structure, the plain one-line notation stored in one array, where we have constant access to each node, each element of the permutation. Then the one-line notation plus the inverse permutation stored as two arrays, where this grants also the constant access to the inverse permutation. And finally, the wavelet tree. So in this table, we have the four data structures that we're going to compare. And as you can see, we have the space consumption in bits, where our the structure takes 3n log n because of the 3-line matrix. And then we have a time comparison of the operations that are handled by the data structures. So if you look at the transposition updates of both pi of I and pi of j into arbitrary elements I and j, we take amortized hologain time. Whereas the one-line plus inverse notation takes constant time. So we are a little bit slower in that department if we just look at these two operations. But when we have to take into account also the same cycle query, or even just returning the number of cycles, we take amortized hologain time, respectively constant time for the two operations, whereas the one-line plus inverse notation takes linear time for both of these queries. The Euler tree in its static form takes very little space, but when we want to update it, there's an unbound number of rearrangement in the underlying bit vectors and rank data structures, so we have to actually rebuild the whole structure from scratch and taking n log n time. So finally, I presented you a new approach to storing permutations and handling quite effectively the dynamic changes in it. And this is useful to track the cycle structure after each update. And as I showed you, we can return pi of I, pi to the -1 of I, and answer the same cycle query and update with transposition the underlying permutation in amortized hologain time, and returning number of cycles in constant time. And that's all. Thank you for your attention.
Thank you very much, Francesco, for a very interesting talk. Are there any questions from the audience?
Hi. Thanks for the interesting talk. I was thinking that I think you can compute pi to the k in log n time too. If you splay the node, you splay I, then you should have, I mean, you need to maintain the size of every subtree in your splay tree. I think this is easy to maintain upon rotations. And then you splay I, you have it on the root, you go to the right child, and then you go left or right, depending on where you will find the kth successor. And when you find it, you splay to maintain the potential function. I think you can do it in log n time too.
I see, that's a very good remark. I haven't thought about it in this manner, but it could make sense. But right now, on the spot, I'm not envisioning how I can possibly know beforehand where I have to end up during the downward traversal. But this is a nice suggestion. Thank you.
It will probably increase the space, knowing the number of elements in the subtree.
Yes, but you can use maybe dynamic parentheses to maintain it, and then you get them in logarithmic time also.
But are you saying in one, Gonzalo, in one go, like you access pi of I, and then you access pi of pi, like the successor of
no.
You splay pi of
you
I.
splay pi of I, and then you go to the right child. I assume you have already normalized the case so that you know it is to your right. Okay. Otherwise, you take the modulo of the size of the cycle where you are. If they ask you pi to 1 million, you first take modulo.
Oh,
but then it is to your right. Okay. So you go right child, and then you go left or right downwards, because you know the sizes of the subtrees until you get the kth successor. And then to maintain the amortization, you splay the answer. You splay the kth successor.
So you want to find that's what my question. You want to find the case successor in one go. It's not like you find pi of I, splay it, then you find pi of,
no,
because that's what we've been doing.
Of course, no, just in one.
I don't think I understand that at the moment.
But
okay.
But we can talk
Afterwards,
later.
yeah. All right. Great. Thanks.
Yes.
Are there any other questions?
Hi. Surprise. No, I was just thinking similarly, you could actually, if you want to transpose chunks, I think that also works because you can, so with display tree, you can actually hack out, like if you want to take a whole big chunk out of a cycle and or swap chunks around, that'll work because you like splay the endpoints. But also, since you can split and join AVL trees, I think you can make it worst case logarithmic time by just doing the same thing with AVL trees, and so I think because there are logarithmic time split and joins on AVLs, so I think you can maybe get rid of the amortization and generalize the transposition operations.
I'm not sure for the proposed option, and just for the problem of doing the cycle rotations, I'm not quite sure if this can still be considering the logarithmic bound, but thank you again for the nice remark.
Are there other questions from the audience? Otherwise, I have a question.
No
Okay.
questions.
So, are there questions?
No.
Okay, so I can ask my question. So it's kind of ugly question, but do you think that you can, for example, represent also compressed representation of permutation? What does it mean? It means that like we know that the Barrows-Wheeler transform, it's a permutation, and then you can compress the permutation basically using Nishimoto and Tabe. So do you think that you can adapt the slide tree representation to the compressed representation and support similar operations?
It's a nice question. So if you were, maybe the idea would be to compress some, I don't know, maybe a semi-runs in the same node, and maybe this could be somehow acceptable. The issue would be how much do I have to pay to then decompress the single nodes, and then to also keep track of the relative position when I rotate a cycle. But I mean, this could be also a nice future outline, I guess.
Okay, thanks. We are right on time, so we can move to the next talk. Okay. So okay. Where is John? Okay. Anna, are you here? Yes.
Hello, can you hear me?
No. Yes.
Okay.
Can you try and share your screen?
Can you see my screen now?
Loading. Still loading. Yes. Now I can see your slide. Okay. So next talk will be given by Sana Kashkuli. It's about the simplify Please, Sana, go ahead.
Okay, thank you. Hello, everyone. My name is Sana Kashkudi, and I'm a master's student at Dalhousie University. Today I'm going to present Simplify, which was supervised by my supervisor, Travis Gagey. So suppose that someone gives us a permutation pi to store compactly such that we can evaluate the pi quickly and easily. So here we have a permutation on numbers from 0 to 44. And here, as we can see, we can recognize a structure of increasing subsequences. And one of the things that we can do is that we can consider these substrings that are increasing, as you can see here, 32 to 35 and 36 to 41, and then again 22 to 31. We can consider these subsequences into a block. Although there is another standard approach which says we can split it into the increasing subsequences and assign each subsequence a character, and then we replace the numbers with the characters of the characters that we are going to assign. And then we can build a rank data structure, and then we can store the offsets like here. And for example, here we can see that we have a bunch of W's and then an X and then another bunch of W's, which we can see, for example, if we want to assign W number, it would be starting from, for example, the fifth W would be 32, 33, 34, 35, 36 would be the value of the fifth W. So one of the ways to do this is using a wavelet tree with sparse bit vectors, but we're going to see if we can use an easier approach. So one of the ways is that we can ignore the sequences and we can divide them into blocks, and we will not use rank or select anymore, and we can treat each of the blocks individually. For example, here we will have 32 to 35 as one block, then 5 as one, 36 to 41, which is another increasing sequence as one block. Again, we will proceed until the end. And then we're going to store multiple values in 4 rows. I'm going to explain them all individually. So in the first row, before I go through this, I would like to mention that these two columns next to each other, which we have 3 of them, these are continue of each other. It's not like they're separated. And the column on the left mentions I, and the column on the right indicates pi of I. For example, pi of 0 would be 32, pi of 1 would be 33, and so on. So on the first row, we're going to store that for each blockhead in pi of I, we will store the index that it will map to in column I. So for example, here, the first block the starting position of the first block will map to 0. So we're going to store 0. And the next block in the pi of I would map to index 4. So we will store 4. Then the next block, its starting position maps to 5. So store 5, and so on. And then we store a string that says how these blocks are permuted to get the I column. So this is the string that we have, and what we're going to do is that we're going to stably sort it. And if we stably sort the string, it will sort the blocks as well. So for example, here we have this pattern, and we can see that the red blocks here in the pi of I column refer to the character Z. And we can see that 32 to 35 is one red column, red block. 36 to 41 is another red block, and here 42 to 44 would be another block indicating Z. So what we're going to do is that we're going to stable sort it, and that means that, for example, we have 3 Z's here. They're going to map to the last 3 blocks in our I column. So we said that the left column is I column. So as we can see, the last 3 blocks here are red, and they are indicating the Z characters blocks. So next we're going to row 3, for which we store the starting position of I's block heads in I column. So for example, here, yeah, we can see that for, okay, so it's like starting position of I's block heads in I column. Yeah, it's just the start position of I's block heads. So it's 0, 1, 5, 6, 12, 19, 22. And as I mentioned before, this is not the end of the block. It is just the end of the column. So we will not go to 15. We will store 12 and then 19 and so on. And then, yeah, 19, 22, 30, 32, 36, and 42. And what we're going to store next is that which block in P of I's blockhead will map to. For example, here, the blockhead of the first block is 0, and it maps to the 0th block in pi of I column. So we're going to store 0. And then we have 1 as the next starting position, and it still maps to the 0th block in the pi of I column. And then we have 5 as the next value as our starting position of the next block, and it will map to the 2nd block. So we're storing 2. And then again, the next blockhead's starting position maps to 2. So we're storing 2. Next block's starting position is 12. It is mapping to this block, which is 0, 1, 2, 3, 4. So we're storing 4. And this will go until the end of the numbers. So what we want to do is that we want to calculate 2 things. First is pi of 9, and the other one is pi of 9's block in the pi of I's column. So for the first thing, we want to know what is the value of pi of 9. And the second thing was we want to know which block in the pi of I column will have the pi of 9. So I'm going to go through all the steps. So first, we notice that pi of 9, actual value 9 is in block 2, because as we can see, 9 is greater than 5 and less than 11. So it's in block 2 of pi. And what we're going to search for next is that we want to know, okay, this block 2 in column pi I, where is it in column I? So we should see where it maps to. And as we can see in this pattern, the second block here has mapped to the 8th block, which is here. So the second block, which was 0, 1, 2, okay. It maps to the position 8, which is 0, 1, 2, 3, 4, 5, 6, 7, 5, 6, 7, 8. Okay, here. And next, we're going to find out what is the starting position of block 8. So the starting position of block 8 would be the value that we have here on index 8. So it is 36. So okay, now that we found out that, we know what is the starting position of block 2, and we know the starting position of the block 8. So what we're going to do is that we are going to add the difference between the value that we had, which is 9, and we're going to calculate the difference between 9 and its starting position in block I, which is 5. And then we're going to add this to the starting position of the block it maps to in column pi of I, which is 36. So then 36 plus 9 minus 5 would be 40. And that will give us the pi of 9's value, which is 40. And as we can see, yes, pi of 9 is 40. And then we said we were going to find out what is the value of pi 9, which is pi of 40. We actually don't want to know the value, sorry. We want to know which block in pi of I column has that value. So what we can see is that 40 will lie between 36 and 42, which maps to block 7 to block 9. So what that means is that this is not giving us a specific answer. This is something that in computer science, they call it finger search. And it means that we're not given the answer that we're looking for, but we are given we are given an indicator that gives us the starting position of what our answer will lie into afterwards. So it will tell us where to start and where to start the search. So for pi of 40, we will have a block from 7 to 9. And as we can see, pi of 40 is 43, and it is actually, since we have 9 blocks, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These last 3 would be our blocks 7 to 9. So it is actually correct because the value of 40 is in block 8. So permutation pi is actually LF, and suppose that someone gives us a permutation LF to store compactly such that we can evaluate it quickly. And what we need to know here is that the values that we stored in the first row takes R log n divided by R bits. And it takes us O of 1 time. It takes us constant time to look up. And we will need R log sigma for the second row. And it will take us constant time to rank as well. And we need R log n divided by R bits again for the third row. And for the last row, we need 12 R bits. And it will take us O of log R time to do the finger search, but this is what it is in theory, and it's not as bad as it looks in practice. In practice, it will be way quicker and faster. So here we have the SA values as well, and we have the so we're actually having some genomes here, and we are given the SA values as well. And for the next example, I'm going to talk about phi of j. And for phi, we need to know that for a SA value, phi is the previous SA value to that SA value. So imagine we have like, let's consider 0. Phi of 0 would be 18, or if j is 1, phi of 1 would be 19. And if it's 2, it would be 38, which is 38, and it's correct. So we're going to apply the same thing on phi. So here at the left column, we have j, and in the right column, we have phi of j. And again, we're going to have 4 rows. And what we're going to do is that in the first row, we store the starting position of phi of j's block head, aligning with the j column. So 18 maps to 0, 38 maps to 2, 20 maps to 3. So we're starting 0 to 3, 39 maps to 9, then 9, and so on. In the second row, we will store the permutation that sorts the blocks in phi of j. In other words, it tells us which block in j the block of phi j will map to. So yeah. So here the first block is 18 and 19 in column phi of j, and it will map to, it says that it will map to the third block, which is 0, 1, 2, 3 here. And again, this is not the end of the block, this is just the end of the column. So the third block in j is where the first block in phi of j maps to. And then for the second block, which is 38, it says that it maps to 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, it maps to the 10th block. And it will go until the end of the numbers. And then we have the starting position of the blocks in the j column, which is 0, 9, 10, 18, 20, 26 until the end. And then we will see where does each block in j will map to the block in phi of j. So here 0 maps to 0, then 1 will map to 0, 1, 2, 3, the third block of phi j, and then again the next value, the next starting position in j will map to the third block in the phi of j column, and so on. So this is pretty much the same thing as the previous example. So imagine we want to find the value of phi of 25. So as we can see, 25 is in block 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. And 25 is between 18 and 26. So it's in the 8th block. And the 8th block that we're referring to is in the phi of j column. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So yeah, 25 will map to our 8th block in phi of j column. And then we said that we're going to see where this block will map to in our I column in the previous example, and in this example in the j column. So as we can see, it will map to the second block. And as we have stored here as well, the 8th index has stored the second, that has stored 2, which means the second block in j column is where our 8th column in phi of j will map to. So next thing that we say is that we're going to find the starting position of this block in j. And as we can see, so we have second block here, and we're going to go to the second index here. So 0, 1, 2, and it gives us 10, which means the starting position of the second block is 10. So now that we know that, we're going to compute the phi of 25. So we have 25. We know the starting position of the column, the block that it aligns with in the phi of j column, which is 10, and we know the starting position of 25. At first we had it was 18, so we're going to find the difference between 25 and 18, which is 7, and then we're going to add it to 10, which gives us 17, and as we already knew, 25's 5 would be 17, which means it's correct. And then what we're going to do is that we want to find the block that phi of 17 will map us to, which means, sorry, the phi of 25 will map us to, which is phi of 17. So we just want to know which block is it, and we want to do the finger search that I mentioned earlier. So sorry, what we're going to do is that 17 lies between 10 and 18. So the block that we're going to find phi of 17 in is going to be 3 and 8. So it's actually true because 17 is here, and we're getting the result that its phi value is between 3 and 8 blocks. So 0, 1, 2, 3, starting from here, 4, 5, 6, 7, and 8. And as we can see, its value was in block 7, which is in the range that we mentioned. So again, we have constant time for lookup, and the finger search takes all block R in theory, but in practice it's faster. And the space complexity for the first row is R log, sorry, R log n divided by R bits, and then we have R log R for the second row, which we have improved it from R log n to R log R, but still not ideal. So we're going to work on this. And the following time space complexities for the next rows. And as the future work, we would like to optimize the encodings, and we also want to implement phi inverse, and we want to find a way to find out the LCPs as well. And we would like to tweak PFB to work with larger data sets, and build R-index with lookup tables, and eventually Wcta. This is the bibliography, and thank you so much for listening. And please let me know if you have any questions.
All right. Thanks very much for the talk. We have time for a very quick question. If there is any from the audience.
Can you hear me?
So,
no.
Yeah.
There is no questions, Max.
Yeah, no, I have one quick question. So basically you are using the finger search, but this does not guarantee you the constant time access, right? For the phi function?
Yes.
Because you don't have the Nishimoto and Tabe's theorem to break up the rounds, right?
Yeah, actually, but I remember Travis was mentioning that Nate had an implementation, and he did some experiments that it showed that in practice it didn't take as much as time that we had in theory. But yeah, basically we haven't yet had any better time.
Okay, thanks.
You're welcome.
Okay, we can move to the next speaker, which should be on site.
Yes.
Pablo Gutierrez, sorry, right?
For transforming a geographical representation of a given object with a certain level of detail into another representation of that same object to map it to a lesser level of detail. Why would you ever want to do this? Well, for example, consider this map that will appear. No. The laser is, I think, I don't know. Okay. Okay. Where was I? Okay. Consider this map at 1/500 scale, whatever. The important thing to note is this is a relative close-up zoom of the coast of Galicia in the northern part of Spain. And for comparison, consider this other map. This is the same coast, but with the zoom farther away. Actually, this area on the first map is around here. Now, the idea behind cartographic generalization is that it is considered that it wouldn't be reasonable to represent every detail needed to draw this visualization, this map, for this one, because the pixels will eventually merge together. You are not able to appreciate, for example, the detail here, the finer details of the coast at this scale of visualization. So the basic idea is to store multiple representation intended for different scales of visualization, right? So for a more in-depth example, consider this grid. And yes, I know this grid is divided into quadrants. Ignore that for now. That's actually a spoiler. But consider this grid and this polyline as defined by these 12 points, A to L. Now, this will be our geographical object, our original geographical object, as defined by all of its detail. And now we can fit this polyline to a line simplification algorithm like Douglas-Peuker and get a selection of the most relevant points and these 8 points that represent a more simplified form of the same geographical object. And this could be, if this is our level 0, the original of representation, this could be called the level 1. These points, BD, etc., that are grayed out, we are not storing them at level 1. This is just for making it more clear visually. Now, we can do this again for a level 2, even simpler, and even a representation with even lesser detail, with only these 5 points. So the basic idea is we, in practice, this is like how it works generally for geographic information systems that use cartographic generalization. The idea will be to store these 3 representations separately, and depending on the scale the user is querying, you use either one or the other. But what's the problem here? Well, for example, these points are being stored 3 times, and these are being stored 3 times. This is the exactly same geographical information, the exact same points, stored multiple times at different levels of detail. This example is very simple. This is only 3 levels. If I recall correctly, most geographic information systems use 15, I think. We have a redundancy problem, right? We are here on a compression workshop. So what should we do with redundancy? We should redundancy, action hero style. So that's the basic idea. We want to propose a solution capable of doing this, of recovering a representation of the same geometry for different levels of detail, but we want to somehow address the redundancy problem. We want to never store the same geographical information more than once, ideally. And also, we want our solution to be able to answer a bounding box query. This is the most basic query for a geographic information system, right? You get a bounding box as defined by x min, y min, and an x max, y max, and you want to recover the points of your geographical object inside that box. Well, in the case of this bounding box, it will be the result will be f, g, h, I, j, and it's important to know that the result should be in that order because this is a polyline. Sorry, this is a polyline. So f connects to g, to h, to I, to g. A result that returns as f, but then g, then h, then in another order, that will not be valid because then we need to preserve the order of the points. We need to be able to preserve the order of the polyline because if not, we are like, okay, we are recovering the correct points, but we are changing the geographical features. If we suddenly connect this f to this k, for example. So this is important to keep in mind. Also, we wanted to highlight that our our solution is called Diamondo, and we are very proud of the name. I may explain the name at the end of the presentation. If I somehow forget, that will be a brilliant question to ask. Wink, wink. So now, before explaining our solution, let me quickly enumerate the pillars of Diamondo because the building blocks, the technologies we will be using. First, we will be using bitmaps, a binary sequence supporting run canceled, and actually the current implementation actually use successor2. This is the first building block. Now we also need a wavelet tree. This definition, these slides are very simple, very basic, because I don't want to dwell for too long in the interest of time. I don't want to dwell for too long with this, but only to highlight that what interests us about the wavelet tree is that we can use it for granting a particular order to any sequence of symbols, and also take note that we will be using a code-based tree. You will see in a moment why. That's the second building block. And lastly, we will be needing a K2 K-square. I'm not sure how to say what's the correct name in English. I like K2 tree. We are interested in its capabilities of an spatial index capable of executing a range operation and recovering the points inside a given range, a given area. Now, these are the three pillars, like the three Legos we will be using for constructing Diamondo. And when designing and implementing Diamondo, we tackle it like in two separate steps. Like there were two challenges. The first one was to store the geographical representation without redundancy, while also being still capable of returning the representation in simplified forms adequate to different scales. So how do we do that? Well, consider this is the same example as before. Consider these three levels of detail. What we are going to do is we're going to build a bitmap for each level of detail. So for the level 0, consider this bitmap of length n, with n being the number of points on the original geometry of the original geographical object. And we will be setting a 1 for each point that it is actually present at that level of scale. So for the level 0, that includes all of our points, is the original representation. We have a bitmap of full of ones, completely filled with ones. Now, for the level 1, we have a bitmap B1, and the level 1 includes the point A, right? So the first position is set to 1. But there's algorithm simplification. In practice, we are using Douglas Poker, decided that the point B wasn't significant for this level of detail, so we keep a 0 at that position, and so on for the rest of the position, and the same for the level 2. So what we have here, and this is a very simple idea. This is a kind of a dumb idea, but with this, if we just store the geographical representation of the object once, the full geographical representation of the object, we can use these bitmaps to filter the queries at any level of detail. Like if I want to query the level 1, I can go to the bitmap B1 and see, okay, I only have to consider the points A, C, etc., etc. We actually tested some other alternatives for doing this, because this was like our first idea, but this was the one that seemed to work the best. Well, of course, you might have noticed that B0 is redundant, because if we assume, and only if we assume, that the most detailed level, the level 0, corresponds exactly with the full geographical object, then the corresponding bitmap will be filled all with ones, so we don't have to store it. If we want to query that level, we just query the original geometry without taking any bitmap into account. Now, that's the first challenge met. Now, we continue on to the second round, round 2. Answer the bounding box query. So, here we have the grid again. And what we are going to do is we are going to treat this as a matrix, as a binary matrix. We are going to set a 1 at the positions that contain points. And we are going to index it with a K2 tree. So This is the resulting K23. And with this, we can actually do a bounding box query and recover the points that are inside the bounding box using the range operation on the K23 implementation. However, we have the problem of on what order. Like, okay, I know that the answer to this bounding box query following the K23 is the point here, 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 but I don't know on what order these points are at. I don't know the original order of the points with this. I need another some other structure to recover the points in the original order, and this is where the wavelet tree comes into thing. Well, we are going to use a code-based wavelet tree using as a code the C order code for every point. Why? Because this is the same order. The ones here in the K23, the K23 index in C order, right? So these ones will be in C order. So if we construct the wavelet tree like this, starting here in C order, the result will be that every leaf on the wavelet tree can be, the leaves are in the same order as the leaves in the K23. So we can align every point here with a 1 on the K23. And this is the complete, the final form of Diamondo, kind of a diamond. You see, no? And now how do we answer that bounding box query? Well, we had, thanks to the range operation on the K23, these ones, and we know we have these leaves aligned with these leaves on the wavelet tree, and we just only need to go up the wavelet tree and recover the original permutation, the original order of the symbol, of the points. Well, the range query is for recovering the points inside the bounding box. And now the wavelet tree can recover the points in the original order. So we know in which order we need to connect the points to reconstruct the correct geographical object. Finally, we can use the bitmaps to filter that results to return only the points that should appear at any level of detail. Now, I have, we actually implemented this like a first draft, first try, first attempt. And I have some preliminary experimental results. These are pretty basic, but I just wanted to have some tables for you to believe me that we actually implemented this. So our test data was, because we wanted a very big grid with kind of sparse data, because the K23 will work with good for this. We indexed the polylines defined the outliers of all the territories of the United States of America that, funnily enough, covers the entire planet. You need a Earth-wide grid to index all the territories of the United States of America. For baseline purposes, we stored this on a PostgreSQL database as a like the basic baseline. And we also did a little compression, just storing, we converted the point values, the decimal degrees point values to integers, and stored them in bitwise compressed vectors using the Simon-Gogg library for C++, the SDSL library, just to get some compression, just to compare us against. The result is, well, because we are only indexing polyline sums, only some of them at that, this is very big. But well, even so, our proposal, Diamondo, can compress roughly, compression rate of roughly 26% with respect to the PostgreSQL database. Is obviously better than the bitwise compressed vectors, because these are still needing to store all the levels of detail. These still have redundancy. Diamondo technically doesn't have redundancy in the because we are storing each point only once, even if we need some additional structures for querying. Some very fast results. We did some random bounding boxes that included some data. We used small boxes, medium boxes, big boxes, and we compared against just sequentially recovering the points inside the box in the bitwise representation, just as a quick test. Our results seem good for the small and medium boxes, but pretty bad for the big bounding boxes. This is actually not because of the size of the box. This is most likely because of the density of points. Because the more points we need to recover, the worse we perform. Now, as conclusions, well, we think the name is good. We want to keep the name. And also, we think the idea of modeling geographical reference data while avoiding redundancy is a good idea to continue researching about it. And well, we think this research topic is promising. Currently, we only are working with continuous polylines. Of course, we want to extend our capabilities to index all kind of geographical features, like polygons. Also, we want to, we were thinking of alternatives to not have to store the full object, the full original object, and also some ways to improve the performance of those bounding box queries that includes lots of points. And that will be all. Oh, sorry, it was just a thank you. And that will be all for my part.
Thank you very much for the very interesting talk. So are there any questions from the audience? I have one quick question. In the meantime, so it's the, can you use the K-square tree blocks to like try to bound the alphabet of the wavelet tree that you use to define the order of the points? Like if like you have some points, like two disconnected points from two different regions of the K-square tree, if you can reuse some letter of the alphabet for defining the order of those points.
Like I don't know if I get that right. Like using the K2 annotating the order in the K23 in any way. You say.
It's like breaking the queries in the K23 such that you can like reduce the size of the alphabet of the wavelet tree.
Ah, okay. Like.
And in some way, maybe this may also like reduce the depth of the wavelet tree and save you some time. I don't know. It's just a suggestion.
Yeah, but that will then we will need different wavelet trees for different blocks of the K23, if I am understanding correctly.
No, you can use the same wavelet tree. You just use different letters, probably. I don't know if this can create a problem. Like you have to remap the letters in somehow, depending on which part of the K23 you are looking at. But
I am not sure.
I don't know.
I am not sure. I need to think about it. But thank you for the suggestion.
Are there any other quick question from the audience?
I have a quick question. So I just want to ask, maybe there are some geographical entities like cities that are just dots, so they don't appear as polylines. So in that case, probably the part of the wavelet tree is not necessary.
Yeah, of course. If we only are indexing dots, or if we are indexing dots for those, we don't need a wavelet tree the order doesn't matter.
So I think these geographical entities that are polyline probably are rivers or streets or coastlines. This kind
Yeah,
of
mainly
thing.
coastlines, but yeah.
Okay, thanks.
Too many questions.
Are there other quick questions? Otherwise, we can move some of the question to the coffee break.
Okay, so what's the name? The story of the name?
Ah, the name. Nice. Good question. So, well, first, the idea was diamond because of the shape of the two trees linked, because when we painted the structure in the board, we painted as a tree, an inverted tree, and I said like, oh, that looks kind of like a diamond. And the mondo part is first because it kind of sounds like mundo, the word for world in Spanish, and also because mondo or monda in Spanish means something that doesn't have any unnecessary part.
In Italian, mondo means world. So
Yep.
you're just
It
correct.
was very good
Perfect.
in Italian too.
Okay, so let's thank then all the speakers of the third session of WCTA again, and we will see at 16:35 for the first and last session of WCTA. Happy coffee break.
Here? Ah, we're back. Here.
restricting them to be expanding lose compression power, but we could not prove that deleting the coding will reduce compression power. We believe that the answer to this is that yes, it will reduce the compression power because the morphisms are crucial to represent not necessarily polymorphic words. Okay. ¿Cómo me pasé? En español. The second open question is if we can support efficient direct access on L space, O of L space. We could store the length of the expansion of the iteration of these morphisms for each symbol and for each level. Well, we cannot do that because that is too much space. Also, the derivation of the L system can has length n, so it can take too much time too. So the following, I need to introduce the following definition. The incidence matrix of a morphism is defined as M phi, and it counts the number of A sub I in the expansion of A sub j. It's called that we always can exponentiate the matrix to obtain the matrix of the exponentiated morphism. And we can use this matrix to compute the length of the expansion of the iteration of the morphism over a specific word by using the Parik vector and the identity vector and the power of the matrix Using these lemmas, this is an old result. Charit and Swart can detect if the iteration of the morphism over a symbol is less than certain value. They also managed to fix the problem of having to traverse too much of the derivation tree of the system. And they solved this problem of direct access in that time. A polynomial on sigma, that is the number of symbols, the t, that is the width of the morphism, log d, and log I. And they also use sigma square space to store the matrix. The problem is that the time depends polynomically on sigma and t, with a big, especially a big exponent in sigma. In our case, sigma can be closer to L than to the alphabet of the string. So that can be a bit too much. And also the matrix use sigma square space. And if sigma is our L system is mainly a lot of symbols, a lot of rules, that will be omega L squared. Some ideas are to use the explicit formula or explicit formulas of Saloma to compute these values. The problem is that these formulas have length sigma, and they are also could be costly to compute. And the other idea that we have is that we try to find some kind of a special form of the system, trying to favor the length of the rules instead of the number of rules. And well, the other problem is trying to approximate L heuristics, but this is really hard. There are not good results about this currently. So conclusion, we proved that L can be much better than delta in some string families, up to a square root n factor. L is in general incomparable to all the other repetitive measures except G. G upper bounds L. Restricting L, the features of L gives worse measures, and nu combines the copy paste and power of morphism in a non-trivial way because we can obtain a space smaller than the minimum between the two. And that and there is the current challenge that I explained before. Okay, thank you very much for your attention. Here are the references.
So, is there any question, Travis?
Thanks. This is a very vague question, so I'm not sure I need an answer right now. But so over the past few decades, we've been basically, if you think about the Chomsky-Schutzenberger hierarchy, right? So you start like regular stuff, or like Markov stuff, regular stuff, finite state machines. Then you go up to like context-free grammars and things, push-down automata. And you have context-sensitive grammars and things like that. And then at the top you have Turing machines. And so we've sort of been moving up from the base to the first level. And because as you go higher, you gain more power, but things become harder.
Yes.
So there's also been, right at the top, you have the ultimate incompressibility, which is Kolmogorov complexity, which is incomputable. But I don't read them, but I see them every so often. People do resource-bounded Kolmogorov complexity. So it's like they're doing something orthogonal to what we do. They start with the most powerful model and then they cripple it. So I'm just wondering if Well, if like we should, as a community, look at that stuff, not me in particular, obviously, but no. So I was just thinking that since, I have not looked at this stuff like Lindenmayer systems. I haven't looked at for well over 20 years. But since you're in, do you also see these bounded resource Kolmogorov complexity papers? If not, I can send you links.
I have not seen this Kolmogorov complexity, but I think we should try to always go lower, staying computable.
Yeah. Well, if you bound the complexity, it does become computable. So anyway, okay. So that was just a vague, like open-ended.
Other questions? So if there are no more questions, we can close.
So that should be the last question of the
Yeah, you had to be.
No, I think you completely correct that Travis.
We should say Travis instead of questions. This is the question. The chairs of Spark 2. Thank you.
Yeah, definitely. I want to thank to Max and Adrian that they did a really great job. Even no one maybe knows, but the designation of the scholarship for students was thanks to Adrian and Max. They make all the requirements, prepare the form, select the people and everything. So thank you very much for that. And thank you. And it was a really nice week. So thank you very much and see you next Spire Europe.
Thank Jose for pulling all the strings behind the scenes, at least from what I saw. It's Max talking.
Yeah. Okay, so with this, we close Wcta, and we hope to see you next year.
Thanks, everybody, for being here.
Ciao, Max.
And thanks, Adrian.
Thank you.